Hello there, thank you for joining me again today on another repair video. Today on the bench we have the Marconi 2955B radio communications test set. This particular model was the last of a 2955 range made by Marconi Instruments. If you check out my other videos, there are videos that I've done on previous models of this, which is a 2955A, 2955R, and then came the 2955B. I think the very first model was just called the Marconi 2955. Yes, I'm right, 2955, and it had a 30 watt port on, and that was the very first model. So it went the 2955, the 2955A, which had some extra features on, including the high powered RF port. The 2955R had a sensitive receiver built in, which is this TX monitor on and off facility, which the 2955A had that blanked off. And then after the 2955R became these, the white coloured test sets that Marconi started producing before it was sold to IFR and Aeroflex subsequently after that. So this is quite a nice looking test set. I recently acquired this from a friend of mine who wanted to sell up some of his test gear that he no longer wanted, and he said that this did used to work. It did used to work perfectly, and then all of a sudden it didn't power on when he connected his mains power to it. I've got the mains plugged in at the back, and sure enough, hit the switch. There's nothing, no sound. There's no smoke billowing out the back, no crackles, bangs, pops. Nothing like that. There's no life at all. None of the LEDs are coming on, which normally come on when the test set first powers up. This particular unit doesn't come with a handle either that attaches to these two screw holes at the side or the feet. So I've got some of those in a box somewhere, so if we get it working I'll attach that. I reckon this has probably been in a smoker's workshop because of the discolouring that's occurred to these plastics, the knobs, and this. I reckon this has probably been some cigar smoker or somebody like that that's been using this test set over years for those parts to discolour like that. I have repaired plenty of 2955Bs for many years now, and they don't often have this discoloration of these plastic parts, so I reckon this has obviously been used by somebody who's a tobacco lover. Now, with regard to the calibration labels on top, they've been obviously screws been removed, so obviously somebody's been into it, so that'll be interesting to see what's happened there. And if we turn it round a moment, just to the rear of the unit, we have the power supply section, which is behind this cover here. We've obviously got the fuses, 3 fuses here, main selector and IEC mains in. So I think due to the fact that there's absolutely no power whatsoever, we'll check these fuses. That's the first thing that needs to be done, to find out whether any of these are defective. There is also the possibility we could try and run it up on DC supply to see whether it works that way. It's something I'm probably not going to do at this stage until I find out which part of the system's at fault, just because I don't want to cause any other issues. The air filters have totally disappeared that normally fit in here. There's normally some like a foam material that goes in there to allow the filtration of air. These have obviously been out because the calibration void if remove labels are broken. So, and again underneath the radio test set as well, I think if we can just flip it up, the feet are missing, and again we've got the disturbance of the calibration void if remove labels, so obviously it's a clear sign that someone's been into it. So what we'll do, we'll just test the fuses, first thing and take it from there. Just do the basic fault finding, basic level fault finding first before we really get into it. So I'll take the fuses out, give them a test, and then we'll whip the lids off and have a look inside, and I'll be back to you shortly. Okay, we're back now. We've had the fuses out and tested them, and they were fine, the 3 fuses. And what we can see at the moment is the power supply section, which is this board here. So this resides behind that big black panel that you saw on the back, and then there's a separate metal screening can that fits over that, which I've removed to expose the power supply. Now this is made up of 2 parts as a power supply: the mains toroidal transformer, bridge rectifier, and 2 reservoir smoothing capacitors are actually on the other side of this, which we're going to take a look at in a moment. They then supply DC voltage to this board. Now this board, which I've spoken about before in the other videos I've done on the repairs of the 2955 series radio test sets, actually performs 2 functions. First of all, it isn't a mains powered switch mode power supply, although it is a switch mode regulator. What it is, it works off of a low voltage input. So there are 2 supplies which can come into it. One from the DC battery supply, 11 to 36 volts I think, that comes in, and the second supply is from the bridge rectifier smoothing capacitor circuit, which resides on the other side, which is the mains supply that's stepped down, rectified and smoothed, and that enters here. And then this relay, this orange relay you can see there, switches between, depending which supply we enable, we'll select between those. So it'll select between mains or battery, depending. If it detects a battery voltage, it'll switch over to that. Then what happens is which we'll look at in the circuit in a second, that is ultimately then fed through to a 10 volt regulator. The 10 volt regulator then provides a continuous steady DC 10 volt supply then to switching regulators, which are mounted on this heatsink here, and I think they're like an IRF 540 or something like that. Switching FETs, and those 2 FETs that are down there actually switch high frequency pulse width modulation to the toroidal transformers that we've got here. They in turn are rectified then and smoothed by these capacitors, which then produce multiple supply rails of varying voltages that go off into the rest of the system. So that's how that works. Now one of the common failures that there is on these power supplies is the switching FETs down here, and these FETs sometimes fail and therefore they can't switch. Now one of the nice things about this power supply, the way it's designed, there are actually some links that connect to the gate of each FET that you can then sample from on the oscilloscope the drive signal, so it makes it quite easy to fault find on this board. It's generally not too bad to maintain. So what we'll do, we'll just have a look at the other side now, where the first stage of the supply is derived from. So if I just try and turn this round a little bit so we get a bit of a better view, unfortunately with this one having the GPIB option on it does make it a little difficult to see, but if I can try and get this light in a bit better, you can probably just see it, but more or less just under this board here and that earth strap there's actually a toroidal transformer, and it's just here. It's like a big donut that's down there, so that's the main toroidal transformer, and then that comes then to the bridge rectifier, which is also mounted right down there. It's very difficult to see because obviously the mains IEC plugs that are here, but you can just see these blue cylinders that are down there underneath this wiring, and they're the electrolytic smoothing capacitors that are down there. So basically you've got in the rear section you've got the toroidal transformer here, a bridge rectifier bolted to the heatsink metal part at the back, and then the output of that's fed to these two blue smoothing capacitors that are down there, which provide steady DC voltage then obviously for the main board, power supply board at the back. Now if we just have a look at the diagram on the PC a moment, this diagram for the power supply can be a little tricky for the unwary, simply because it's difficult to find both parts of the power supply on the same diagram. They're on two separate diagrams at opposing ends of the manual, which doesn't help. But basically, I can just get the mouse pointer to show a moment. If it will let me do that. It doesn't seem to like me selecting a pointy finger, it wants a cross instead. So what we'll have to do is use our magic screwdriver to indicate. So let's see if we can get the camera steady. Okay, so what we've got here, first of all we have the mains filter IEC socket on the rear, which is this. This obviously is fed via two separate fuses for the live neutral path. Then it goes straight to the front panel on off switch, which is at the front. Now that switch serves two purposes. It switches the main supply, and also it switches the what would be the battery volts on and off as well. It enables that, so it's a double function switch. Then what happens is that's get fed to the toroidal transformer on the rear, and obviously the toroidal transformer has a voltage selection switch to alter different taps to select different portions of the primary side of a transformer for different voltages for international standards. Then what happens is it goes into a bridge rectifier, which is bolted to the back, and then we have the two reservoir smoothing capacitors there. So that's basically what that is. We've got two 4,700 microfarad capacitors and an inductor between those two as well, which isn't referenced, given a circuit reference there, interestingly enough. That then passes out on PLB to the power supply section on the rear, and so that's what we'll have a look at next. Okay, so we're looking at the diagram now for the mains power supply. As we can see here on the left, we've got inputs there, which are derived from the sockets on the back of the radio test set, one of which is the battery supply that comes in, and the other one is external and internal. They represent external and internal feeds coming in, supplies, and what happens is when the battery is enabled, or the supply coming in, this circuit down here at the bottom then actually gets a feed, a power feed via resistor, and then it's also connected, one half of it, to the one half, should I say, of the power switch at the front. As we talked about earlier, the power switch serves two purposes: to switch main supply on and off, live neutral, but it also has another ganged output, which is then for the DC side, and so that uses this transistor switch down here, and then obviously the relay coil is here, which then is energized if it's using a battery, and then it will throw those contacts into a different position to allow the battery supply to come in. But when it's not using a battery supply, the relay in the normally open position, or when it's de-energized, the coil is normally in that position, in that configuration with the switch, so it allows external DC from the mains power supply section to come through, and then ultimately it ends up at the 10-volt regulator section. And this then is a series pass regulator, which regulates the supply that's coming in, be it battery or from the main supply. The step down rectified and smooth DC coming in, then it basically reduces it to 10 volts. And the output of that 10-volt rail then from this transistor is fed out to what is then the main pulse width modulator chip, which obviously deals with all the switching and everything. And if I can just get to the diagram again on the computer and move it along. After the chip, obviously the supply is then fed to the FETs, the switching FETs. Now if I just back out the zoom a second, just so they can see a little bit more, what we can see is the supply rail continues onto these transistors, and that is obviously what feeds these drivers. This is a link I was telling you about that can be disabled. You can remove these links, then you can use your oscilloscope on the outputs of these to check that the drives on both these are switching properly, to isolate any faults in these circuits here. Now the supply, if you like, that's fed to the main switching transistors is a center tap on one of these transformers, which is fed from up here, which we'll look at in a moment where that comes from. But basically those two FETs, that FET and this FET, switch at very high frequencies as decreed by this IC here, and the feedback that it gets, which we'll look at, and that's what controls the output voltages, which ultimately will go out. So if I can just go up to here, we follow that rail round. So as I say, we've got a center tap on the transformer, which has got a DC supply. If we follow that back round all the way along, we've got some inductive transformer which gives some feedback, obviously, to this chip. So it's sniffing the main switching supply rail, and then obviously that is fed down then to the input of the 10-volt regulator. So we'll measure the voltage here shortly as what it should be, but basically after this 10-volt regulator, that's to then supply as a voltage reference, obviously for the IC and the driver stages, but the FETs themselves work on a higher switching voltage, which is pre the 10-volt regulator. So for example, if this is 35 volts DC, for example, when the mains is rectified, for example, the step down voltage from the mains transformer, that could be going along here and then going to obviously these two FETs. But this IC will work from a constant 10-volt supply. Obviously if it's battery voltage and you've got 13.8 volts, that's all that's going to be on that rail as well, 13.8 volts, to be switched here by this. So I don't envisage this rail to be high voltage, but we'll have a look at that shortly. Also there's another section of it which is for overcurrent as well. Got another supply going out there or coming in. Looks like that's a control side. 5-volt regulator as well, so voltage references and supplies off for other parts of the board. And we also have the optocoupler isolation here, one there, and again that's for the air amp. And then also further up we've got as we've seen there, the FET drives, the FET switches. We've got the low volts line as well, which is controlled by this transistor. And we have a low voltage output, or low volts detect. So yes, we're gonna first of all, I think, just for quickness and easiness, we'll just get our DVM onto this collector on this area, on this transistor, which looks like it's a PNP. So we'll go straight onto this rail here. We will check then to see on this emitter here whether there's a supply there, and then obviously afterwards to see if there's 10 volts. That'll be a good starting point, I think, on this particular problem. And then at least we know then, if we're not getting any supply there, we can start looking elsewhere and seeing what potentially could be causing the problem before that. Looks like we've got a clamp Zener, some kind of protection circuit just before it as well, and then obviously a big electrolytic capacitor as well there. So looks to me like as if we can just go for that transistor, just have a look, see what we're getting on that 10 volt regulator before and after, and then go from there. So I'll be back shortly. Okay, so we're back now with the unit powered up. We've got the on-off switch at the front in the on position, the mains supply connected in, and so now we're interested in just measuring some voltages. If you recall earlier, there was TR10, which was the voltage regulator, which was that, was it TR5, was it? 10 volt regulator. Yep, TR5 at 2N transistor there. So, and just before it, there's an inductor L9. So I found L9 and that clamp diode, that D23. So if we just come back down to the circuit, L9 is here. That's TR5, and then that diode, the clamp diode. Can just get some more light onto it extra. This lamp will move. That clamp diode is just down here. It's just there, D23. You can just see it right in the centre of the screen. So if I go first of all to the top of that coil, and let's just see whether I can get a voltage on both sides of the coil. So we'll just go there and just try and move this meter so we can see it. That'd be a good idea. Right, so if I just go on to the top part of that coil, get there. So see if we've got voltage. Yeah, the earth lead's just dropped off, so I'll reattach that, and we're back on the probe again that occasionally gets stuck, and it's terrible. This need to treat myself to some new ones. There we go. Right. Okay, so we'll just go back on there on this coil, top of the coil, see what we get. And that's strange. Doesn't appear to be anything there. So I did see a voltage there earlier. What I did, I removed this cable and then reconnected it, and then although now I notice that there's appears to be no let's have a look here. Might be that it's some kind of timed thing at the front. Let's have a look. No. Yeah, so what happened there was, before filming the previous section, this here is the input to this board from the bridge rectifier, smoothing caps on the other side, and the battery supply. And what I'd done, just to do a bit of fault finding just before I shut the video, is I unplugged this and measured the supply here. And there was a supply coming in, and I know when I reconnected this, it went sparky a bit. It went, you know, obviously there was some current being drawn, and I thought, right, we've got a supply. And I went onto that inductor with my voltmeter, and it measured 24 volts DC on both sides of the inductor, and indeed the diode down here, which is a clamp diode on the diagram, that D23 there, that itself had 24 volts on it. So then I proceeded to obviously you know, shoot the video as we've just doing now, and then there was no supply. It had just gone. But interestingly enough, even when it did have the supply 24 volts, it wasn't powered up, wasn't powering up. So but now I'm not even getting an input coming in here, which suggests that there's a fault before this board. I mean, also obviously when this was getting power and it was going via that inductor, I also measured here, which is TR5, and TR5 is the 10 volt voltage regulator, which is down here. If there's TR5 there. So I just went straight on the collector of that transistor. I went dunk straight on there, and then we had 10 volts on the meter. So the 10 volt regulator was working, and we had a 24 volt supply coming in from the rectified mains, but it still wasn't powering on. But the point is, of course, now that's gone. There doesn't seem to be any supply coming in now, and I don't know, it just seems strange that we've got all these problems suddenly just out of nowhere. So I think I need to trace the steps back now to the other side, which will mean me having to take off a GPIB board out so I can get to the donut transformer. I think as well, the chap who owned it before me, I think at some point the mains toroidal transformer has been replaced. Sorry, the mains IEC filter, and the reason why I think that is because it's not the correct shape for that hole, and the Marconi filters completely fill the void there, which seems strange to me. Also, there's an additional reefer type mains filter cap connected here. The mains filter on the back of that is normally shrouded in like a rubber boot on the back of that. So yeah, it does seem a bit strange to me, does that. Looks like as if there's been somebody in doing some work on it. But I need to get down to that bridge rectifier that's buried deep down there, and the junction of those smoothing caps, the blue caps that are down there, just so I can get on them and measure some voltage directly from there, and go from that stage back, I think. Okay, so what we've done now, we've got the rear panel off, which is the power supply section. Obviously we've got the power supply board here, and then on the inside, as we were discussing earlier, we've got the the mains section, and obviously the mains transformer. Somebody's obviously replaced the mains IEC because we've got this mess here. I know what's happened here. The original mains filter IEC socket that was here has gassed off. The reefer caps inside have vented out, and that's what's caused this mess. Interestingly enough, I had a Roden Swartz signal generator only last week that I've done a video on with the same problem, except in my case it vented out the back like a Roman candle firework. Black, jet black smoke at an enormous rate made this sort of sound with it, like the thing we're going to go up in a ball of flames. And then I had to fumigate the workshop. I had to open all the doors and windows for hours on end, and the stench that comes out of these mains filters when they flare up it's like a skunk, and unbelievable. The stink that it caused for days on end. So I fully sympathise with whoever had this before, who had to replace this. I'm not very happy about the mains wiring not being insulated. I'm going to take some time now to insulate that, either with heat shrink tubing or electrical tape. I don't like mains supplies being exposed conductors. I mean, we've gone to the trouble there. Marconi are putting rubber boots on the live and neutral fuses, and again, whoever repaired this should have done the same there. That is the replacement for the mains filter capacitors, obviously, which is acceptable. But yeah, so just getting back to the original fault. Obviously we've got the mains transformer, the reservoir smoothing caps. I was trying to find the bridge rectifier and I'm looking all over the place. Normally most equipment, bridge rectifiers stick out at you like a sore thumb. You know, it's like doom, and it's there, you know, you can't miss it. It's like just a big black square bolted to the thing, you know, and all the wires go to that, and it's very difficult on this one to see it. But it's actually a round bridge rectifier, believe it or not, normally the square, and it's actually down here behind this this capacitor here. We've got the two yellow wires, which are the secondaries from this mains transformer coming out. One going to this side of this circular thing, and the other going to the left side. These wires here are all the mains input selections, different voltages and things, but basically the primary connection, and then the secondary coils are the two yellow ones. And there's some kind of weird, it's a bit strange to see it unless I go in with the magnifier. Maybe the magnifier might help pick it out a bit better, but some kind of weird, very oddball kind of bridge rectifier which is hidden underneath this capacitor. You know, Marconi have done a really good job of hiding it, and so I'm going to remove that that capacitor there. You can just see down there there's like a cap across the mains. The black cap underneath is across the main the supply secondary supply input there from the secondary side of the transformer, and then the bridge rectifiers, that's that round thing. I think what I'm going to do is just going to go straight on top of those reservoir caps on these terminals, and I'm just going to measure to see what voltage we get there with the mains fed at the back. But I'm not going to do that until I've adequately insulated the IEC socket for obvious reasons. But yes, we'll see what we get there. Right, we've got the mains plugged in now, and the power switched on from the front. We're across the reservoir caps with the AVO meter, the DVM, and we're not measuring anything at all. There's absolutely zero coming out of it with the switch on the front in the on and off position, no matter which. So it looks like we've got a mains problem here with the look of it, as if the main supply is not getting to the transformer. So I'm going to check out the fuses again, just in case something's happened where it's popped one of the fuses. Then we'll pull the rubber boots off those fuse holders, and where the brown and blue wire are there, which are coming out in this section, we will measure those again to see whether there's a supply going to the transformer. Obviously behind that red cover here, just behind there, is a voltage selection switch, which puts the correct configuration for the transformer windings on the primary side, whichever country you're in. Obviously we're in the UK here, so we're doing 240 volts. Sometimes behind those red covers I've had them where the wires desolder or come off the contacts and you make intermittent connections. I think this does have an intermittent fault on it, simply because earlier on I got 24 volts DC across those capacitors, but measured on the connector that goes from there to the other board, and now it's gone. So I think there's one or two faults on this with the power supply. I think there's a genuine fault on the power supply board as to why it's not working, because earlier we did have a 10 volt regulated supply that I found off camera, and also L9 in the power supply had 24 volts DC fed to it, which comes straight from these capacitors. So I reckon we've got two faults. A problem with the board anyway, because it wasn't switching and thus powering up the unit, the switch mode supply side, and I think the other fault is the main supply side. I think we've got an intermittent fault somewhere which is preventing the mains voltage from getting to this transformer, or perhaps the transformer's defective, but we did have something earlier. So I'm siding on the probability that there's going to be a defect with the actual, more likely to do with an intermittent connection somewhere, something minor which will resolve, but yeah, back shortly. Yeah, we've got an ever stranger fault on this, which is puzzling me a little bit. We've got it on mains, well, we're looking at the mains voltage coming in, and we're only getting 18 millivolts, and where we're taking our supply from, basically, or our measurement point, is the back of the mains IEC socket. So I'm across the live and neutral terminals on the IEC there, and there's absolutely nothing coming in. Now this lead here I've changed over because I had another lead plugged in, and I thought perhaps the fuse had gone in the plug, so I put a fresh lead on, and I'm still getting the same issue. So I think there's some dry joints on that. The wiring looks terrible anyway. I'm going to smarten that up a bit. I'm going to reflow it all, and then I'm going to take it from there. But if I pull this out and then measure with my prongs in the IEC, I'm getting 240 volts. But on here, after the socket, on the back of it, I'm actually getting next to nothing. And I've wiggled these about and connected them on different parts of the connection as well, just in case there's any flux or high resistance part of it, and it's still reading 18 millivolts. So I'm going to resolder that, and then we'll take it from there. But yeah, very strange, weird problem. So these bizarre things that can happen, I suppose. So I'll be back soon. Yeah, what I've also noticed as well is with the probes connected across the IEC and the mains removed, put the meter into ohms, so we'll be measuring what will be the resistance of the primary coil on the primary windings of the mains transformer. With the switch at the front set to the on position, naturally the live neutral are then connected through to the primary coil of the toroidal transformer. And as we can see here on the measurement, we're measuring infinity impedance, so resistance. So there's definitely a broken connection or a broken path between the IEC and the transformer. So whether that's via the main switch at the front, I'll have a look at that next. But I'll reflow these, as I said just a moment ago, first, because I'm not getting mains coming in, so whether there's a pin broken in the socket or whether there's some other thing or whatever, I'm not sure, but I'll reflow those till I get 240 volts on this side of the connector, and then we can start from there and then carry on. So it just seems weird, this very strange fault, unless one of the pins in the socket's broken, which might explain why it worked earlier when I'd plugged the mains lead in. It could be that the socket's got a fault on it and that it's got an unreliable connection through it. So I'm going to see if I can fix that first, get the 240 volts back on the back here, and then let's trace it from there. Okay, I've been led a merry dance with this, and I've found out what the problem was. I was measuring, or trying to measure, mains voltage coming in on the IEC, because we weren't getting any voltages anywhere else, and couldn't get a thing. But it's a good job I didn't touch it with my fingers, because I would have been in for a bit of a surprise if I thought that it wasn't live, because it actually was. Turns out the cheapo meter that I've been using for years, this thing, now doesn't read properly. It's not reading AC voltage at all. As a matter of fact, when you connect the probes up here and try and use it with the mains, when you touch the probe on and off the contacts on the socket, it makes a little bit of a clicking sound inside, like a relay is trying to energize, but there's no readout on here, nowhere near what it should be. So, you know, it can lead you down, as it did me, down the garden path, thinking that there's no voltage in the circuit, and there actually is. So, you know, that's a lesson, even for experienced people. You know, test gear can go faulty from time to time. This is a cheap Chinese meter, I think, that I've had for about 10 years now. But I've never had a problem with it before, not that I can recollect. Anyway, we've got a proper meter on the job now, a fluke, can't beat the good old fluke, and so we'll just check the mains. Is coming in on the IEC, and let's just see if I can get on properly. And there we are, we've got 247 volts coming in, nice sine wave. So I think now we can get back to where we were earlier, now that we've got a working meter, and we can look at those reservoir capacitors now behind there and see what voltages are on those. But yeah, that's a very interesting thing. That doesn't often happen to me. Occasionally the leads get damaged, you know, they break internally and things like that, and you can get problems that way with multimeters, which I've tried different leads with this. But the thing is, at the end of the day, you don't expect that kind of a fault to occur. So, you know, it's the meter itself that's failed, not the leads that plug into it. I've had the odd scope probe that's going to open circuit, the coax, you know, because it's got kinked or trapped. Or, as I say, the wire breaks inside the leads and causes a problem. But generally speaking, that rarely happens with me. But for a meter to actually fail internally is something else, but I suppose it does happen. So that's another reason why, even when mains is connected in here and I use a process of elimination by connecting a second lead up to it, and that still wasn't working, you know, I think the message here is don't go touching unless you're absolutely 100% certain that there's no voltages there. And it's a lesson for all of us that you can't always trust test equipment that you're using when it comes to mains voltages. So, you know, always make sure that you test twice, basically, if you're uncertain, and don't take it for granted that the circuit's not live, especially if you've got a mains feed in, and go grabbing hold of terminals and connections thinking that there's no voltage there, or that it's safe to do so. So that's a very rare example of what can happen. And so, right, we'll get on measuring the capacitors. Right, we'll just powered it up, connected the mains, the switch on the front is in the on position. So we've got, you know, ready now to do a measurement. We've got the negative probe on that side of the negative side of the capacitor down there. So I should be able to just go onto that terminal there and measure, and the cupboard was bare, 0. So looks like as if it's the transformer's not energizing. So I just need to check now to see whether we've got continuity between the IEC lead and the what is the transformer when it's in the on position, and I can do that using the ohmmeter side of that, just to check to see if we've got a full circuit or the fuse is blown or something like that now. So we'll do that. Right, so we can't get any voltage across the electrolytic capacitor, and I just had to look at the diagram again. There's no voltage there with it in the on position, and what it is, when we look at the diagram, if I could just move that light out of the way a bit, and let's have a look, see if we can explain what's going on. We can see there on the transformer, obviously with the taps on it, the bridge rectifier D1, and then the two big electrolytic caps, which are the blue caps we've just been looking at, which are the 4700 microfarad. You'll notice that the negative side of the bridge rectifier goes via an inductor between those two capacitors to pin 2 of PLB, whereas the positive side of the electrolytics goes to pin 6 of PLB. It doesn't connect straight to the bridge rectifier. Normally, on most power supply circuits, the positive side of the electrolytics will connect to the positive side of a bridge rectifier, but this doesn't. So they're only brought into the circuit as a smoothing agent when something else happens. So it's not like there's a link between those two at the moment. So we'll now need to look at the next diagram, bearing in mind that pin 5 connects to the I think it's pin 5. Let's just zoom in a bit more. I think it's pin 5. Yeah, pin 5 is on the far left. That goes to the bridge rectifier, whereas pin 6 goes to the capacitors. So if I just see if I can get to this, because the way that they've done the service manual, this is page 1 of 30, and yet the actual diagram that we need to see for the power supply is on page 29 of 30. So instead of putting them together, like, you know, make it easy for everybody concerned, they just make it harder. Right, so if we look here on that section there, we have got, let's have a butcher's. So again, we've got pin number 5, which connects obviously to the bridge rectifier, goes through that resistor, and then to the on-off switch, which goes to the front panel, as we can see there. And that then controls a transistor switch, which activates the relay coil, which is RLA there, which then obviously moves those contacts. So pin 6 and 5 need to be connected together for internal DC in order for those reservoir caps to be brought online. So in other words, this switch has to be thrown into that position. So we're linking here to here in order to connect pin number 5 to pin number 6, you see, of the supply. So it's only when it selects internal DC, and it does that obviously through the on-off switch circuit here, which goes to the power switch on the front, and that puts an active low on that line, which then, using these transistors, biases it into what would be to energise the coil of that relay, thus throwing those two contacts together. And interestingly enough, when I had it connected earlier, it wasn't you know, clicking the relay, so we might have a problem with the relay. The relay is actually on the other side of the power supply section. It's that big orange relay there on the main power supply board. So what I might do, because I've noticed that when this connector here is connected in there, it keeps blowing the mains fuses. Now with that disconnected, I am actually getting the transformer powering up and everything's okay, so it's not like as if it's before that. So I think whatever's faulty on here is causing excessive current consumption, and it's perhaps causing the fault. So I'll measure this next and see what supplies we're getting on there. We've got more strangeness now with the negative lead of the probe connected to that reservoir capacitor, which goes directly to the negative side of the bridge rectifier, which is just down the other side. It goes onto these wires, and I'm not getting any voltage at all on any of these wires. So very strange indeed. These are obviously pin 5 and 6, and then some other you know, from the back panel type lead as well that goes from this DC socket, an earth, and then an on-off switch input. Now what's interesting about it is that you can probably see that little capacitor that's in the top right, and it's a 220 microfarad capacitor. Well, that 220 microfarad capacitor, interestingly enough, is actually over the bridge rectifier itself directly. And if I go on to that capacitor, which is this, that's directly over the bridge rectifier. So if I just go on to, if I just get onto that, which is down here somewhere, let's have a look, see if I can get on it. I'm actually getting 27 volts DC. It's a bit tricky getting onto it because it's obviously a bit of an awkward position trying to get the probe onto what is the lead of the device, because it's got some heat shrink on it as well, which just leaves a few millimeters spare before it goes into the capacitor, and I'm being careful not to short it out against the cam. As we can see there, I've got 26.5 volts DC across the bridge rectifier, but if I now go to what is any of these wires on there, doesn't matter which one I go to, I'm not getting any voltage. And from what I can see, one of the wires which comes through the back plate there, it solders directly over to here anyway. So that's interesting. I'm just going to remove this screw that clamps this capacitor down, get that out of the way so I can see more of the wiring. But there's definitely when I go on that socket, there is no voltage whatsoever on there. So a very strange occurrence indeed. So if I just put that there a second, and then we can see whether we can get any voltage. But doesn't matter whereabouts I try and make contact with it, there's absolutely no DC volts at all on any of those pins. So it just seems strange to me that there's nothing on any of those pins, and obviously this black wire there is actually directly soldered to the negative side of the bridge rectifier, and then that I think is the on-off switch, enable as well, on-off, which it won't be on at high or low unless it's getting a voltage fed back anyway. So yeah, there's no voltage on any of those wires, so I'm going to look at that next. I think take the cap off the bridge rectifier and just peel it back and have a look, see what's going on. Right, so with the probe connected onto what is the negative input on the power socket, that's where the earth connects. That's pin number 6, and on ohms it's reading dead short. Now if I go on to pin 5 as well and read that, that's also dead short. The other connection there, which I think goes to the open side of the relay contact for external DC, that's reading open circuit. So I think if we look back at the diagram a moment, I think that the crowbar diode, that D23 there, just after those caps, it could be the caps as well, you know, there could be a short circuit, but where L9 is on the far left there, if I go on to L9, which is, if I can zoom out again, L9 is this coil just there, that's L9. So if I go on to just onto that side of the coil, we've got again a 0 ohm short circuit. So I think looking at that, I think it's D25, I believe. Could be wrong. Let's have a look. Yeah, D23 is it, or D20? Can't quite make out on the diagram, but I think that is actually there. I think that's it. If I can get the damn thing to zoom in. Yeah, D23 there. So I wouldn't be surprised if that short circuit, and it's definitely reading short there. So I suspect that it's going to be this crowbar diode that's gone short circuit. So what I'm going to do is I'm going to remove it from circuit, just lift one end, just to see whether it's that. I think that's the other capacitor that's in line with it, and I think there's another capacitor somewhere. It could potentially be this one, but I suspect this is short. So I'm just going to remove that from circuit and then come back to you and see whether we clear that short circuit. Okay, we just moved on a little bit now. We've done some desoldering and we've got the scope meter set to continuity. Done a little bit of fault finding in between shooting the last video and this. If you remember, we were discussing just shortly prior to this stage that I thought that there was a short circuit of the diode down there, which is this D23, and that's just located there, and that diode is actually okay, believe it or not. So much to my amazement, I thought that diode had actually failed, but it's actually working okay. Anyway, there's still a short circuit on that supply rail that comes in. I've removed this capacitor as well because I've had these fail before, short circuit, which you'll see in my other Marconi videos that I've done. These are common for short circuiting. So I've removed that. This big capacitor is obviously on the same supply rail. But just looking around, obviously, I found something that I think may be the reason why. This supply rail, obviously, as it comes in, ends up going through one of these transformers, ultimately, and the winding goes back to this switching transistor. Well, the switching transistors are IRF 540s. If you look at the insulator, which is behind each transistor, we have what is a rubber silicon mat, basically, to allow the heat transfer from the transistor to the heatsink whilst providing insulation. But if you were to look at the plastic insulator, which separates the screw and this, it's melted. If you compare it against its neighbours, it's clearly melted, you see, and it's all splayed out. So I'll see if I can get a better view of that for you. If we go right in, I think we should be able to see that a bit better. And as you can see, it's definitely melted. As a matter of fact, some of it has discoloured the tab at the top of the transistor. So you can see that there, whereas its neighbours, they've got quite a very clear cut lines around that plastic. That's slightly melting, but it's not as bad by any stretch of the imagination. Now at this stage I'm not sure if a transistor's actually gone short and then it's overheated and thus created that melt, or whether it's just generally got hot due to operation and has then melted through that plastic, and then it's gotten short circuit. So I need to look at that next, see whether we get away with replacing those transistors or not. But yeah, interesting. Definitely some melting gone on there for that to be like that. Now I've obviously touched the tab of the transistor with the continuity on, just between here and the heatsink, and it is short circuit to the heatsink, which it obviously shouldn't be. So I'm going to remove this now and check for short circuit again, because the gate, drain and source are connected here of this transistor. One side goes to the supply rail that's derived through this, or comes through this transformer, and then the other side is to ground, basically. So I need to find out if this transistor is short, this FET's short internally, or it's just this that's shorted it. Looking at its neighbour here, I think there's definitely been some overheating going on. So I'll come back very shortly with my findings. Okay, I've removed the two transistors that were there, and the shorts disappeared now when I measure across D23, which is here. That line down there is you know, obviously where the positive comes in, just down here, D23. Now with the short gone now, because the transistors I've taken them out, I've just been looking to find out which transistors actually faulty out of them all, but that one's definitely short circuit. This one is fine. It's not short circuit, that one's okay, but I'm going to replace both of them anyway. But yeah, these are definitely, that one in particular is definitely short circuit. I'm not sure at this stage if it's damaged the drivers, so one of the next tests I'm going to do is test these transistors here to see whether or not it's damaged those. I don't think it has, because I've done some transistor testing, obviously you know, obviously with the drive side, just to make sure the gate, drain and source, so there's no short circuit between the gate, for example, and the drain and the source on either transistor, even though one of them's working okay. So I'm fairly confident at this stage that it hasn't gone drain gate short or source gate short. Obviously one side of it, which is the source, is connected to ground or chassis, and the source is connected to the supply rail. So we'll have a look at that now on the diagram on here. If I just zoom in, try and make it a little bit more readable, and we'll just see if we can get this thing to move across. Right. So where that regulator is at the moment, which is the 10-volt regulator, this part of the circuit here, this has a feed fed off it just before the regulator, which is a PNP transistor, and that's fed up this way and along, all the way along. There's obviously a feedback type arrangement there, transformer, and if I try and go along, I might be able to do it, depending on if this diagram will allow me to. Yeah, I think it will. Yeah. Right. Now then, so that's the first transistor. If I can get zoomed in a bit. So we've got the supply coming down from the top, goes to the centre tap of the two windings on the transformer there on the primary side, and with one feed off then to the second transistor, and then another feed off up to the first transistor. And we've got two removable links there, one there and one there. And those that 2N2369 I think it is, and the other transistor, I can't make the number out of, a BC 307As I think they are. That particular, those two push-pull configuration provide the square wave drive to those transistors. So I'm going to test those transistors next, see whether there's any issues. Obviously I remove them out of the circuit because of other components, diodes and capacitors, which again by various feedback arrangements can cause issues, so I've taken them out of circuit for that reason as well, and I'm glad I did. But yeah, so I will be back when I'm going to look down my parts drawer for some more IRF 540 transistors. See if I can find any of these. I've probably got them in stock. I've definitely replaced these before. I've looked in the components drawers that I've got in the workshop to see if I've got any IRF 540s. I think I've put them away. I have lots of transistors in boxes and things, so I'm going to have to start searching through those rather than order them, because I've definitely got them, but it's just finding them. And so what I'll do once I've got those transistors, I will obviously come back to you and see whether we can get this thing working. Back soon. Right, before we fit the transistors, the new ones in circuit, and do some more testing, I think it's just a bit of story time. Considering what we've been through, I found the section in the manual that details all the technical description of the board. It says that the power supply unit, PSU, is a switch mode type which operates from either AC mains or an external DC supply. The rear panel mounted transformer, rectifier and smoothing capacitors reduce the AC input to 24 volts DC before applying to the PSU. Outputs from the PSU are on a regulated plus 12 volt, plus minus 12 volt, plus minus 5 volt lines, which are isolated from the DC input. If both AC mains and DC supply are connected, the AC supply will provide the power. In the event of a mains power failure, the DC supply will be automatically selected without an interruption at the instrument operation. Now, under section input power selection, it says when the instrument is turned on with only external DC connected, the current on the on-off switch line through D29 to C29 is sufficient to pull in relay RLA, which is obviously this orange relay here. It is then held in by the current through R48 and R49 and selects the input on the external DC line. D28 across the RLA solenoid ensures that this selection is not made if a DC is supplied with incorrect polarity. If a DC input of greater than 34.7 volts is applied, Zenodiodes D11 and D12 conduct, thereby switching the relay to the internal DC mains position, and so protecting the PSU. If AC mains is also connected, the rectified input on the internal DC line through R52 switches TR19 on. This causes TR18 to switch off, removing the drive to the relay, and power is then supplied on the internal DC line from the rear panel transformer, rectifier and capacitors. The 10 volt regulator consists of TR2 to TR5 from a series regulator which pre-regulates the supply in order to provide 10 volts DC for controller IC1 and to supply the drive for output switching transistors TR13 and TR16. It says TR3 and TR4 form a Darlington pair. TR2 amplifies TR3's output to provide the base drive for the series pass transistor TR5, which is TR5, if I can find it, is this one. It then says potential divider R12, R46 and R8 across the regulator output enables the output voltage to be sampled by the base of TR4. It says when the DC input drops below 8.5 volts, the sampled voltage also drops, switching TR4 off. TR3 is clamped by Zenodiode D1 so that current still passes through this transistor. TR6 is switched off by TR4, which takes the base of a PNP TR9 low so that it switches in the on position. This connects the dead line pin of controller IC1 to the reference, which switches the controller off. When the DC input falls below 10.8 volts, the voltage drop across the series regulator element TR5 drops below the VBE of TR1. This is preset by R46, which turns off. A signal is thereby sent via opto-isolator IC4 to the processor board AB1 on the low volts line, so that the front panel settings can be saved in anticipation of a complete failure of a DC supply. Now for the controller, it says C6 and R17 are the timing components which set the internal oscillator of controller IC1. It says that to free run slightly higher than 156 kilohertz. After the instrument has been switched on and the 10 megahertz crystal reference on AC1 board has started, it says the 10 megahertz clock input is divided by IC2 to 156 kilohertz, which is applied via isolating transformer T3 to TR7 and T8. These transistors form a latch which turns on every cycle of the divided reference, connecting the timing resistor R17 to earth. IC1 mirrors the timing regulator resistor current into C6, which charges to a threshold determined by IC1. IC1 then discharges C6 and the resulting pulse through C5 turns off a latch to await the next cycle of a divided reference. In this way, the frequency of the PSU is locked to the crystal oscillator. Thus, interference frequencies generated by the PSU are predictable. C10 and C19 provide a soft start facility which limits the line surge current at switch on. In the output stage, it says the controller IC1 provides two non-overlapping complementary square waves on pins 11 and 8 to the driver transistors TR11, 12, 14 and 15. These transistors provide the drive necessary for the highly capacitive gates of the output field effect transistors TR13 and TR16. The purpose of D7, D8 and C25 and D9 is to clamp the drains of TR13 and TR16 to 75 volts. So for the rectifiers and smoothing section, it says the square waves from the secondaries of transformer T1 are first rectified, then smoothed by inductive capacitive filters. Schottky diodes are used for rectifying the plus 5 volt and minus 5 volt rails. The minus 12 and minus 5 volt rails have clamp diodes D25 and D24 to prevent overvoltage in the event of a no load condition. Now for the air amp, it says the plus 5 volts and plus 12 volt rails are stabilised as a pair. The average voltage obtained from R41 and R42 is compared by IC5 with the reference voltage generated by D31. The resulting error signal is fed via opto isolation IC3 into the error amplifier IC1. C15 and R39 and C35 are frequency compensation components. C30 and R58 are hum blocking components. So for the current sensor, it says the supply current is monitored by T2 and is added to the supply voltage with R34 and R35 in such a way as to approximate the product of current and voltage. Thus it is possible to monitor supply power regardless of the applied external voltage. If the PSU is overloaded by more than 20%, the voltage on IC1 pin 16 will equal that on pin 15, and the PSU will shut down until it is producing approximately 120% of its normal output of 44 watts. For the fan drive, it says this comprises a high power Zener D26, which conducts while the fan is drawing stall current. When the fan starts running, the current through D26 ceases and flows instead through R56 and R57. Now there is a DC filter on board AR4, and it says that this filter prevents noise generated by the switch mode power supply from feeding back to the rear panel DC supply socket. It is a wideband filter with the low frequencies suppressed by C1 and the high frequencies suppressed by 2 low pass filters. So that's the end of a technical description or theory of operation of a power supply, which you may be interested to know. Obviously it's useful information for anybody who hasn't got a service manual. At least that audio description might be able to assist them further in fault finding. So story time over. Let's put in the transistors and see what happens. Okay, just to explain where we're at now since the last part, these two IRF 540s that were here had melted these plastic insulators, and what I've done, I've replaced them with two new ones, good quality. These are from International Rectifier, none of the Chinese counterfeit rubbish that you get these days. And then what I've done as well is I've put some new rubber silicone mats underneath them, which are the insulators, the rubber insulators that are just behind, and they will hopefully better the thermal heat transfer. Now the old ones were quite perished, so what I've done, I've replaced the rubber silicone mat things that go behind them to give a heat sink, put new plastic insulators on and fasten them on. Now we've still got a fault on this, which is just in the latter stages of fault finding. These two transistors are driven via these links, these blue links which detach, so you can measure the drive signal to them via these transistors here as well. So these transistors drive push-pull a square wave to these two IRF 540 transistors. They in turn switch via this transformer. So this transformer gets a common supply which is fed via another current limiting or monitoring transformer, one of these, which allows that monitor the current consumption of a circuit. So if it's consuming too much current, it then shuts the drive signal down to the IRF 540s, thus protecting the switching side of the power supply. So I've still got that problem, which I'm going to go into shortly to show you. Now the thing is, the outputs of the supply I've disconnected anyway. This is a wiring loom that goes to you know, the different points on the board for plus 12, minus 12, 5-volt rails. I've disconnected those anyway, just in case there's something external of the supply that's causing a failure. And also we can now start looking at this section of the circuit. This is the main transformer though here, which is what we'll be looking at on the diagram shortly. But what I did, rather than set power supply running to be powered by mains, I've actually powered it through DC, and that saves this awful problem that we can often have where we get an avalanche of current, because obviously the mains transformer and a rectifier with the smoothing caps just provide one massive avalanche of current into this if I were to power it from mains. And that would then, you know, if there's a short condition or a problem, it could destroy these transistors, and then we're back to square one again. So what I've done is I've set a current limit of 3.5 amps on a DC power supply which connects in here. So if we look at the DC supply, I'll just put some more light on. Now we've got current limit on this set to 3.5 amps. We switch the test set in the on position, so the moment when I introduce this is what happens. So you can see it's limiting, it's trying to fire up, and then the relay just clicks, but the fan's not trying to start either, you see. That's the thing, the fan's not trying to go. Normally if the supply was partly working and then shutting down, this would be doing that, you see. It'd be trying to whirl, and it isn't. So I think we've got another major problem to do with this transformer or some part of the circuit around it. Now obviously I've turned the current up a little bit higher as well, but not too high because I don't want to cause damage to these transistors. And this heatsink is getting mildly warm now, so I can tell, you know, that it's driving those transistors quite hard. Now we'll just show what drive signals we're getting here. I'll remove these links so that these transistors are not driven and thus in a short condition in this transformer, and we'll just have a look to see whether or not with what the drive signal is and what the frequency is and what it looks like on the oscilloscope. But yeah, so it could be there's a short turn in here, coil, or it could be, you know, that the frequency is not correct, what's being driven in these transistors, and thus it can't regulate properly. It could be that, could be external components around this as well that's short, could be caps that are short on the output, so it's driving the output into a load that's too high and thus shutting the supply down. So there's lots of different things there that could be going wrong. But if we just have a look at the diagram for a moment, let's see if I can get the camera to focus on the diagram. I'll just shift this out of the way so I can get to the diagram. I'll just zoom in a fair bit, and then we've got the current regulator section just there where it says current detection. So if I can just zoom into that part of the circuit, so there we have the transformer there, which looks like it says T2 to me. which detects the overcurrent, and that then is obviously fed onto the, or fed off the emitter of that 10 volt regulator. So that's getting the full supply that's coming in externally, and that is fed off. If we can just get the diagram to move over for us so that we can see the switching side of the circuit. So that gets fed here, and what we've got is we've got the two switching transistors, and then we've also got this transformer, and the centre tap of a transformer is actually what gets the constant feed, which is derived from this line up here, which goes from that transformer there, which is a current detector, comes down to the centre tap of that transformer. So the top transistor, and you can see the jumper there, where it says PLC. The top transistor switches one half of the coil, if you like, on the primary side of that transformer, and then the bottom transistor there switches the bottom half. So now if I remove those links, which we can do, and power the circuit again, if current consumption's there, then we know that will be via the transformer and those diodes, and that circuit down there at the bottom, which potentially could have a fault condition. So we'll have a look at that, but I'll also have a look at the drive signal that's leaving those two transistors and what the frequency is. We'll have a look at the theory of operation, but it could also be the fault condition as well on the output of a transformer, which could also be causing this fault condition. Now there are two supply rails which are fed off, which is on the top rail there, and then the second supply, I think it's the 12 and the 5 volt rails, and they go downwards, and they're fed off to by an optocoupler to this IC for a positive feedback. So again, the short condition could actually be in that part of that circuit there. The output may not necessarily be on this section. So we'll have a look at that next and see where we get to. Okay, we've got a drive signal there, as we can see, of about 73 kilohertz, and quite a nice, good, solid drive signal of 5.4 volts. So that signal I've taken directly from the jumpers. If you remember, just shortly before we were looking at the jumpers on the board. Now that's where we are there. So we've taken the this jumper here off, and we're measuring the drive signal that leaves these transistors and drives these. Likewise, we've got another jumper here which I've removed. So that's where we're taking that that signal from, that we've read down there. Now the thing is, 73 kilohertz, I'm not sure until I read the manual technical theory of operation as to whether that's the correct frequency or not. So that's the next thing to look at. But what I'll do is I'll just move the probe over now to the other one. Now obviously, with it being a switch mode power supply, we are actually looking at the input side. So we're taking our earth, which is that black crop clip there, from the input side negative, not the output side negative, which is down here. When we're measuring the output side in this area, the negative connection is actually here on the output, which is on the negative section of this, because they're isolated. So just be aware of that, and then you're not making any mistakes. Right, so let's have a look, see what signal we've got we do have a signal, and so it's the same as before. So I'm happy with the drive situation that's coming into those two IRF 540s. So the fault could be anywhere, or a fault. So I think I can look at now testing these diodes. Got into the diagram, there's a cluster of 1, 2, 3, 4 diodes per output. So I can see 2 diodes there, 2 diodes there. There's a couple of diodes there, and there's probably some others as well hidden around here somewhere. So we'll have a look at those, we'll check those to make sure that they're not short. Potentially we could have shorted electrolytic capacitors. That's something else I'm going to have to look at. May have even a short winding on this transformer. Well, when we look at the diagram, we should be able to isolate different windings on that transformer. If we look at the top side, between the middle tap and the top tap, I could isolate that. I could just remove the top tap there, pin number 1 I think it is on the transformer, which goes off to the top transistor. I could remove that and then see whether the bottom half of the transformer there between pin 2 and 3 on the primary winding of the transformer is okay. Now I've got an LCR meter, so I could measure the inductance of each half of that coil to see whether it's uniform or not, whether it's a direct short or an open circuit. I doubt it'd be an open circuit because we wouldn't have any current consumption if that were the case. Now what this does prove, this test that we've just done now with the drive signal that we measured here on these jumpers, which we've just removed, is had there been a short circuit with these diodes D7 and D, I think it's I'm not sure what that is, could be D6, D8, whatever, I'm not sure, that BAY72, and these diodes here, if there'd been any faults in that area, even with the jumpers out, that fault would have still persisted, and it's not. It's only drawing 9 milliamps on the power supply. So with it only drawing 9 milliamps, and it's obviously giving a, you know, a square wave drive, then I'm happy that the conditions that we've been looking at here around those components are okay. So I think personally either the primary windings of that transformer are short on one side, so I could just put the jumper in on the bottom or on the top, and then I could then drive it, because that's equivalent to removing the tap on that coil on pin number 1 and pin number 3. That's the same as doing that by putting a jumper in on the top transistor or the bottom to drive either one and see whether the fault still persists. The other thing to do then is to start looking in this area, see whether they've got a short inductor, those smoothing inductors, whether they've got some kind of a short somewhere to ground, because sometimes they're encapsulated in a metal frame which is soldered to the earth. We could have a short winding on one of these outputs, so that's another thing that we might want to look at. So that's where we're heading for next. I mean, at worst case I could disconnect the coils on the secondaries on both those windings to see whether or not, you know, we're getting a drive signal through the transformer. So to rule out the transformer, the primary and secondary coils has been an issue. So there's a few little things that we can do here. So I think the first thing I'll do though is probably install the link on one transistor at a time to see whether or not it's the primary windings, and if it does look like it's that, then I can measure the inductance of the coils. Now obviously this type of transformer is a custom built, specialist wound. The bobbins that are in there are specially wound, Now I could, if it is short circuit, send it off to a specialist transformer winder that I know of, who will then be able to rewind it for me, because I would imagine there'd be the same number of turns on both sides of the coil. So that's a potential fix for something as custom as that, because that's a very specialist component. But hopefully it's not that, touch wood. I doubt it would be, but you never know. If a transformer has been driven by a lot of current continuously because the transistor's gone drain and source short, and it's allowed a flow of current to go through the transistor continuously into this coil at DC frequency, which is obviously going to provide a lot of current, not at the frequency that we're currently looking at, then this could burn out in theory. Now I've had a look round this area to see whether I can see anything obvious that may have burned out, you know, the usual thing, black charred diodes or you know, that kind of thing, but I can't see anything of that nature there that stands out. There's no burning smells or anything like that. I'll have a sniff on this transformer to see if I can smell the usual burned enamel or you know, copper wire smell that's burned up, but I can't, there's nothing that sort of stands out at the moment at me. These capacitors look in good nick, but if you remember the previous Marconi 2955 repair videos I've done, I've found quite a few, particularly the smaller caps, that have gone directly short, so there's nothing to say these haven't gone short as well. These are the filters, output filters. Potentially we could have a short circuit to earth with the solder connections on the pins. It's doubtful, but you know, so many faults are obvious little things. You know, we could have a short via the former to the outer of the device onto the board. So there's all sorts of different things that can happen there. It could be a short cap. Could be so many things. So we'll need to delve further now. So many possibilities. The starting point will be to attach a link on here to one side, so we're driving one transistor only on one half of a coil. Let's see if we can rule this out, and then from there we can start isolating everything else, and then we'll move on. It's one of these things though where, you know, even if there's a short circuit on the output and I put one link there, this transformer ain't going to be able to provide an output, and then the sniff back via the optocoupler into the chip still going to shut it down. So really I'm probably tempted to just lift one of the center tap on this transformer and measure the inductance from one side to the other to confirm that the inductance of the primary side of the coil is correct before proceeding, because driving this with just one link at a time isn't going to establish whether it's the primary on the transformer really. It's if there's still a fault condition on the output on the secondary side. So I need to really look at the inductance of the primary coil on this device to see whether the primary coil's dead short. So I think that's what we'll do first, to be honest, rather than faff about doing a lot of other things that have been meaningless. So I'll be back shortly. Okay, we've desoldered the taps on the transformer now on the primary side, and we're reading on one side 30.2 microhenries, and that's basically between pin number 3, I think it is. Let's have a look. Yeah, I've got pin number 3 down there, and on this on that leg there's pin number 3. This connects, if you like, to the centre tap of the transformer, and this is then pin number 1 is that one. So we're reading 30 microhenries on that side. Let's just see if we can get on this solder blob. A bit of a mess that when it came off. It didn't come off cleanly, so I'll have to tidy that up when it's put back on. But it's like a weird tape type copper they've used. Right, so we'll test it again, and we'll just see what it comes up with, and hopefully it'll be a similar inductance. Yeah, so I don't think the primary side of that transformer is defective. I think it's okay. Both reading 30.2 microhenries inductance. So I think I can safely say that the primary side of that transformer is okay. So we're probably looking now at more of a chance of a short circuit being on the output stage of the secondary side of the transformer. So I'll need to now look for shorts and other problems. So back soon. Okay, we're just looking at the theory of operation now for this power supply, and it says output stage. It says controller IC1, which is this, provides two non-overlapping complementary square waves on pins 11 and 8 to the driver transistors TR11, 12, TR14 and TR15, which are obviously these. It says these transistors provide the drive necessary for the highly capacitive gates of the output field effect transistors, TR13 and TR16, which are these two IRF 540s that are down there, you see. It says the purpose of D7, D8, C25 and D9 is to clamp the drains of TR13 and TR16 to 75 volts. It's obviously the back EMF of this. So then it talks about rectifiers and smoothing, which is this sort of section here in that area. It says the square waves from the secondaries of transformer T1 are first rectified, then smoothed by inductive capacitive filters. So that talks about these inductors and capacitors here. Schottky diodes are used for rectifying the plus 5 volt and minus 5 volt rails. The minus 12 and minus 5 volt rails have clamp diodes D25 and D24. And it says that that prevents overvoltage in the event of a no load condition. So, you know, that's some diodes that clamp it down. Error amplifier. The plus 5 volt and plus 12 volt rails are stabilised as a pair. The average voltage obtained from R41 and R42 is compared by IC5 with a reference voltage generated by D31. The resulting error signal is fed via opto-isolator IC3 onto the error amplifier of IC1. It says the resulting error signal then via C15, R39 and C35 are frequency compensation components. It says C30 and R58 home blocking components. So the current sensor, it says the supply current is monitored by T2, which is this device here, I believe. It says and is added to the supply voltage with R34 and R35 in such a way as to approximate the product of current and voltage. Thus it is possible to monitor supply power regardless of the applied external voltage. If a PSU is overloaded by more than 20%, the voltage on IC1 pin 16 will equal that on pin 15 and the PSU will shut down until it is producing approximately 120% of its nominal output of 44 watts. So that's a little description anyway of the theory of operation of this power supply. I'm not entirely convinced at this stage that we've got a short circuit on the output. I'm not convinced of that. It could be that we've got an opto-isolator IC problem, feedback problems, that kind of thing. I just need now to put it into a condition where we've got a low current limit on the power supply, so these transistors don't get too overdriven, and to start monitoring what's coming out of this transformer onto these diodes, see whether we've got something there. I'm just going to measure on the output of a diode to see if any of these filter caps are short, or we've got a short on the output somewhere that I've not picked up. That's the next thing I'm going to do. Just off camera, I've measured these diodes, these 4 anyway, just to see whether or not they were shorted, but they're not, they're fine. So I'm just going to do a little move now over to this side of the circuit, because we've concentrated quite heavily on the upper part here, the primary side. I'm now going to look at the secondary side, see whether we've got any short circuits. And the easiest way to do that is to go onto the output of the diodes directly and check them to see whether there's any short circuits that way. But it could still be a feedback loop issue rather than a voltage regulation issue or a short. But these transistors were getting quite warm and seem to be taking quite a lot of current. So I'm still in the mind that there is a short somewhere, or something clamping something. So that's what I need to look at next. Back soon. Right, we're back with some more developments. Just looking at the diagram and what we read earlier with the theory of operation. Down here, if I can get it to focus, which it doesn't appear to want to do. Well, we are at last. If you just have a look there, D24, that Zener diode, which is on the -5 volt rail. Now, this Zener diode here is a 6.2 volt BZ whatever diode, and as we can see there, one side of it is on the supply rail, and the other side is to the what is a chassis connection, which is the centre taps of the transformers. Now, in the theory of operation that I read out earlier, this diode and that diode clamp these. So if there's no load on these rails, instead of them going very high, these clamp that rail to keep the voltage regulation in check. Now, I've just gone on to this diode here on my meter, which we'll just have a look at here, and it's actually just see if I can get some more light on it. This damn light that I've got, let's have a look. It's just down there, and a bit difficult to see at this stage, but there's a diode down there which is see if I can zoom into it without the magnifier. See if it'll get that. It just don't want to zoom in sometimes, this camera, it's a pain in the backside. Let's have a look. Let's see whether it'll zoom in, but basically there's this diode down here, which is that Zener diode, and the Zener diode that's in this location is appears to be short circuit. Now if I look at the probe on the multimeter, we're on ohms at the moment. If I go on the earth side, the one that goes to chassis, it reads obviously 0 ohms, but then if I go on to the side that goes to the supply rail that it's meant to clamp, It reads 0.01 ohm, so that's definitely a short. And that supply rail is feeding. There's a terminal down here. It's just a shame I can't get the camera to focus. It plays up, this camera, sometimes. Sometimes it's great, it focuses without a problem. Other times it's just an absolute bastard. It don't want to do anything. And this is just one of those times. The autofocus has just stopped working on it. Just totally stopped working. It does this from time to time. While it then suddenly it'll start working again. But there's a terminal just here, which is the supply output for that side of the power supply, and that's short circuit as well. So yeah, that's obviously something that I could have picked up on earlier when I was looking around, but I was looking for supply voltages. I'm sure I did actually go on to each of the terminals to see whether there was a short, but I must have missed that one. I've done something wrong. I've missed that. I've definitely gone on to the other terminals, but obviously there were multiple supplies. I'm sure I'm trying to measure in ohms on them all, but anyway, if I go on to that terminal now with my meter in ohms, I think I might have oh yeah, so I'm on that terminal, and it's yeah, it's reading differently. If I go back onto that diode again there, yeah, so across the diode it's reading short, but on the terminal itself then it's yeah, it's reading short as well. So I don't know, I missed that. I must have missed that earlier, the terminal there. I don't know how I've done that. I've missed it anyway. And there is a short circuit with that Zener diode then. So yes, we'll whip it out and see whether it is that short circuit, or it's something else along that line which is short. There could also be, you know, some other component on there which is short. So unfortunately I'm going to have to take the power supply out again, and I don't want to do that because I've just put lots of white silicon heatsink compound on the bottom of these transistor where the bolts through. There's a big metal plane that bolts to the back of the instrument for the heat dissipation to be wicked away, and there's a big aluminium block under here that's, I've put some fresh Dowcore in heatsink compound on, and it's really messy stuff. It goes all over the place, and that's all going to have to come off again while I get the board out to desolder it, which I'm not looking forward to doing, but anyway, we'll have to do it. So back soon. While we're waiting for the desoldering station to warm up, I've just switched it on. Just noticed something in this this area. You might be able to see it on camera, but if you look carefully at this capacitor, just trying to get the light right, you can see there's a bit of damage to it. Just here, there's like a dent in it, as if something's impacted it at some point and dented it in. Well, that's that diode that I couldn't focus on earlier that's down there. And that's diode 24, the Zener, which I'm just about to try and unsolder, and this is the output terminal here. But I am now thinking, before I unsolder that Zener diode, it's going to be harder to get out because they bend the pins over on the board. They've bent them over, so it might be easy to take that electrolytic cap out and test that, even though, because I'm looking at that, it's got a considerable amount of damage there, as you can see, and I'm wondering if it's gone short because it's physically damaged. The can's been impacted in somewhat there, quite significantly. So I'm going to take that out first. It's going to be easier to remove those two legs than the bent over pins for the Zener diode, and with it being a glass bead Zener diode, I might break it trying to get it out. You know, you never know. So I'll take this out first, because that's definitely got signs of significant damage on it as that. We'll measure this first, I think, so bear with me. Anyway, the plot thickens. All is not what it appears. We've removed the damaged capacitor, the one that's got the ding in the side of it, from the board. It's a 2200 mic at 25 volts, and anyway, it works. There's nothing wrong with it. It's says there capacitance 2275 microfarad, so it's okay. It's still in spec. So despite it having a big ding in the side of it, where it's been impacted just there, quite a significant dent in it, it's still alright. But over to the power supply board now. The diode has been lifted, which is just here. I lifted one end of it up, and that appears to be okay as well, which I'll show you on the meter in a moment when I can get it to stop moving. It's faffing about. So let's have a look. Right, so I can just get some more light on it. So we've got the diode just lifted there, up at one end, and if I go just to check the earths and everything are connected properly, if I go onto the earth side of it, the meter reads 0 ohms, you see. Now if I now go on to the other side of that diode, which is lifted in the air, this side, I can see that it's reading megohms, so it isn't short circuit. But if I go onto the terminal that stands at the side of it, which is this terminal here, then we are reading a short circuit. So we'll look at the diagram again. But so the Zener diode's lifted, the smoothing cap's out of circuit, which I don't know if it's related to that particular part of the circuit, which I'm sure it is when I look at the print on the other side of the board. The C24 as well, because according to this part of the diagram, I think it said that the C22, I think, oh, that's a lot, it says 1000 mic there. So there's a 100N, and that says 1000 mic, but it's actually a 2200 microfarad capacitor. That's a C22. So is that C22? Let's have a look. I have no idea. I can't see a legend on the board for it. That's C24, I think it is. Let's have a look. Yeah, that's C24. I can't see a legend on there. So there's not much to go wrong, really. Oh, hang on. There we are. That's C22. Well, C22, according to the diagram, is that one. Then we've got the inductor, and then we hit the diode, which is D22. See, if that diode's gone short circuit, then it'll obviously pass, allow, when we're testing on the terminal there, we've lifted this diode now, that's open at one end, so there's no way that can short. That capacitor's out there, that C22, so when we put this ohm meter on, current flow can technically go through this diode here, which is diode 22, if it's short, and then end up back to the centre tap, which then is the earth loop, so then we can effectively get a short that way, or likewise we can get a short across that diode via that coil to earth as well. So a couple of possibilities there to look at now. So I need to have a look at diode 22 on the board, which I think I think it was under these cables here. I think it was one of those, I think. Yeah, diode 22 is there. So maybe that diode there has gone short circuit, and that's diode 21, is it? Yeah, diode 21. So diode 22 and diode 21 are there. So technically, yeah, could be those two diodes then. Could be those two that are short. So I need to take those out of circuit now and just double check to see whether they're okay. Bit of a nightmare really, that, getting the two diodes out here. One of them came out fairly easily with the solder sucker, you know, and it sucked all the solder off with no problem. The other one though, to the right, was an absolute nightmare, and believe me, there was a lot of swearing going on while that was getting removed. Interestingly enough, I got some dental tools, yes, dental tools, which I bought some years ago quite cheaply from a stainless steel supplier in Sheffield, not too far from me, who makes these for the dentist industry. And they're great little tools, I tell you. If ever you get a chance to get on some order some dental tools. And I think I have some other tools somewhere as well that's used in pathology when they're cutting people up for autopsies and stuff, and they have all these little gadgets and tools for pulling bones apart, and you know, various other things they do to people under post-mortem autopsies, and they're really good electronics tools. These I think are dental, I'm not so sure. I think they are also medical as well, because there's some scalpel types that are very sharp amongst this as well, and some weird bent sort of tools as well that have are not like dental. So I think it's a mixed set. I think it's used as a demonstration set for the salespeople who are selling it to the medical industry, but they're medical grade steel, stainless steel, probably very expensive. I mean, goodness knows how much these were to buy brand new, but I got these really cheap because of the fact that the company who was making them closed down or ended this production line or whatever. So I got the opportunity to get these, but great for getting electronic components out, and they've got all kinds of fancy little bends in them, and ways of being able to pry things gently without having to, you know, get a pair of pliers and yank things and that. So that's just a bit of a sort of a crossover really in tools between the medical industry and the electronics industry. There are some tools in electronics that you can get that do resemble you know, obviously dental tools as well, but they tend to have plastic insulated handles on them and things, because they're used for adjusting things in live circuits. So it's not recommended to use stainless steel tools in live applications where a circuit's powered, because obviously could short things out or get electrocuted. But for removing components and assembly work and doing intricate work with fine wires and things like that, you know, we've got all kinds of little hook things, and you know, you name it, it's all there. But it's just you know, a great little tool set to have. So I've used this to try and pry off this damn diode, because the diode that was in there didn't want to come out, and the amount of solder around it and things had just prevented it from coming out. So now then, if I go on to we've got the earth again connected here onto the negative. If we go on to this diode here, which is I think it was D22, we're reading 52.6 kilo ohms, so that's not short circuit. Now if I go onto the other diode, then that's the fault, dead short, zero ohms, so that's the short circuit. So that's the fault there then, which explains why the power supply was closing down, because this has gone short circuit. Now we can confirm that by moving obviously this probe onto that terminal, so we're reversing the flow of current to check both the diode both ways, and we'll go again onto here, and again it's now where is it now? Oops, not on right. I need to be on there, because that connects to that LAN down there. So yeah, it's short circuit. So we can definitely tell that component's failed there, which is diode 21. It's gone completely short. So I need to find one of those in my parts bin and replace it. So back shortly. Hello there, we're back again. I looked for the Schottky diode, which is those two diodes there, D22 and D21. Only one of them was short circuit, the one on the right. So I replaced that. I managed to find one in my Marconi spares cupboard, and put it all back together thinking it was going to work. Powered it back up, and it was still faulty. It was shutting down and trying to restart, and the relay were clicking away, and it was drawing a lot of current. So I took the current limit on the power supply set low just so that I didn't damage it. So I started looking round again at the output stage, and what I did, this transformer here, the primary side of the transformer goes via those two red wires. One's to the supply rail coming in, the other side connects to this transformer via the two transistors, and so this transformer has two coils, and it forms a current sense transformer. And we'd already removed the primary side in the earlier video with the inductance measured on the meter. We had a meter down there, which is what we used to measure the inductance of the coil with, and it wasn't a short circuit. Anyway, we progressed on then, and what I did off camera is I did the same with the secondaries here, because none of the diodes then were defective. One diode's mounted on this heatsink here, which is that one. That's for the 12 volt rail, and then the other rails are low current ones, apart from these 4 diodes here, which I think is for the 5 volt rail. These two Schottky diodes here are for the minus 12 volt rail, I believe. But these rails that are basically unregulated as such are clamped by a Zener diode. There's a Zener diode just down here, which is diode 24 there, and then there's another diode, just a couple of diodes there, which you can see just there, which regulate, clamp if you like, the rails if it's offload the power supply, which it is at the moment. and I couldn't find what was wrong. You know, I was pulling my hair out a little bit, and anyway, I looked at the diagram again, and I was almost going back to the stage of you know, looking at the transistors again around that area, and I'm glad I did, because I noticed something that I've not checked, and I'll just show you on the diagram on the computer. And it was quite a simple thing, but if you miss it, it can be a bit odd. Right, so if I try and zoom in for you onto the thing. Now you'll notice there are two diodes, the BAY72s right in the centre of that transformer, and they connect together, and then the top side of the diode on either side goes to the transistors. Now they're only little you know, glass diodes, BAY72s. They're not Zener diodes or anything, they're just fast frequency switching diodes. So what I did is I got the multimeter across them, and to my surprise they were short circuit, dead short, both ways. And what's strange about it is if you follow the circuit down to that diode there, that Zener, that BZ, I think it's a BZ V85, what that does is it clamps that transformer rail, if you like, what goes to the transistors, to make sure it doesn't exceed 75 volts, you see, on the peak. But I noticed something else that's strange as well. If you look at the components beneath, you've got one end of the diode connected to ground, but also then you've got three components as well connected to the ground side as well to chassis. So that's strange, because normally I'd expect to see those components connected to the top of that diode, not the bottom, because the bottom's to chassis anyway. So unless there's different earths or something and it's going to a different earth, which it looks as if it is, because they're all legend with a box with 0 written in, whereas the square box with 1 written in for the grounds there on R31, and as well as that diode, that BZV85, is in a 1 in a box, so there must be different earths. But still, yeah, just noticed that. But with regard to those two diodes there, so what was happening is, with the diodes both being short circuit, effectively the top and the bottom half of a transformer were trying to be switched by one transistor, because it's in a push-pull configuration. When one transistor is conducting one way, the other transistors are being driven the other way, so it's quite a unique setup. But those two diodes were short circuit, so we had that diode down there, D21, which goes across from pin 7 of the transformer on the secondary side to the input of that L7 inductor. But D22 was okay, so it was just D21 that goes across. That was short circuit. This diode that's in that dotted line, that 20CT045, that's actually mounted on that heatsink. So that's actually to the left on that heatsink there. It's signed diode 18. You can just see it there under that sticker. But the three transistors, if you like, the two on the right are the main switching transistors, but the one on the left is a diode, which is bolted to the heatsink. So that is that diode 18 there in the dotted line connecting to L5. So we had that D21 short, and I thought I fixed it then. You know, I was you know, running around the workshop happy clappy and you know, singing and dancing, and turned the damn thing on, and then it wouldn't bloody power up. So you know, it was back to square one again. But yeah, so those diodes had gone, So what I've done, I've replaced those diodes. I've got a BAY72 somewhere, but I can't find it. But I've actually replaced them with a better diode, and the ones that I've replaced them with are a BA 159s, BA159s, and they're the BA159s. Down there, those red coloured diodes, you can just make them out. They're just there, look, just in front of those two transistors, and they've got a higher frequency and current switching frequency and current rating than the BAY72 diodes. So anyway, I looked up the data sheet on the web and came out with some fairly useful data, because these are fast recovery rectifier diodes, the BA159s. So I've been using those two, and now it's up and running. Now we're getting voltage coming out. So I've just got to set this potentiometer here for the 10 volt regulator. So that sets the 10 volt regulator, and I believe that potentiometer sets the 5 volt rail. But the power supply is offload at the moment because obviously I've got the leads disconnected. So I'm going to reconnect those, and then we're going to see what the voltages are and adjust the pots, you know, to get the correct output. And then it's a case of seeing what else is wrong, see whether there's anything else wrong with the test set, run a self-test, see if it powers up properly without any errors or problems or fails, and go from there. I've got another mains filter as well to go here, proper mains filter, so we'll fit that next as well and restore it back to its original condition. Back soon. Okay, we're all powered up. It's drawing 3.18 amps. The test set, when I turned it on, it made a click with the attenuator like it normally does on these models when you turn them on. Seems to be coming up. So I haven't looked at the screen yet at the front of the test because it's on the bench long ways going that way, so I'm going to have to turn it around once I put all this back together again and have a look. But just going on the 10 volt regulator, and I can find my probe. It's hiding on the collector of that transistor. So we've got 9 point, no, the lamp's always isn't weighing it, 9.99 volts, that's alright. So we'll look at this line now, and let's go on to there. That's the minus 12 volt rail, minus 12.38. This one down here is plus 12 volts. There's a little smidgy one over here. You have to be careful not to short it out on that pot at the side. What's it called? It's a pain to get on it, but once you're on it, you just got to be careful, that's all. And that's the other thing that you've got to do as well. You've got to put the earth on this side, because obviously it's isolated. So just do that before we go any further, otherwise we'll make a mess of our measurements. Right, I go back on there. It's always a difficult one to get on, that one at the bottom. Pain in the backside is that. I don't know why Marconi put it there. So that's minus 5 volts there. And then the red one up there, red supply, plus 5 volts there, 5.1. So I don't really need to do any more adjustments. I'm not going to twiddle this pot, I'll leave that alone. If it ain't broke, don't fix it. That's my adage. But we'll just go and check the instrument state now. I'll just assemble this back panel back as it was, put the mains filter in, and we'll just see whether it's the fan's running anyway there, so that's whizzing around. So I'm quite happy at that. I don't think these transistors are getting, now they're just lukewarm, so they're okay. So I'm quite pleased now that at least the power supply is running. And it was a pain in the arse, that power supply, it really was. I mean, I've repaired hundreds and hundreds of 2955s over the years, and normally the faults with the power supplies are just these two transistors that pop, and very rarely do you get any other faults. Actually, they're normally very reliable, the power supplies. But can't say I've ever had to replace any of the diodes before on them. I don't imagine that, you know, it's a common thing, but this particular one, I think it's been flashed. Something's gone on with it. I've had numerous faults and problems that I haven't seen on other instruments like it, so whether it's a fluke or whether, you know, I know other hands have been in this before me, so it could be that something occurred and it's obviously caused further damage or what, I don't know. But anyway, I'm going to put the back panel back in situ now, back into the frame, button it all up, and then we'll have a look at the self-test feature and see whether or not the CRT is powering up. I think it is, because I can see a bit of a glow back. I think I can see a bit of a glow back anyway from the front of the bench, so we'll see what happens now. Back soon. All assembled back more or less now. Got the GPIB in, the mains filter, put a new mains filter in, everything's all connected, so I've got the mains lead plugged in, so now it's just a case of turning it on and seeing what happens. Just get some light on the subject. Right, hit the switch. So we've got screen. Right, let's have a look then. See if we can turn it round without blowing it up. Let's have a look now at self-tests. See whether it passes its self-tests. So I've got to help, and then self-test, all tests. Let's see what passes and fails. And the intensity works okay. Touch wood, it'll all pass its tests. If not, something else to look at. And at least it's powered up and the monitor works. That's half a battle. It seems to be going okay, although it can always fail at the bottom. Oh, it's passed them all, my goodness. Can you believe it? Oh, very good. I'll check the RF gen levels and in the next part of the videos now, and do all the tests for the duplex, the tones, the TXRX monitor, sensitive receiver not fitted, so it doesn't have that fitted then on this particular model, so it's not like they are then. So that was still an option then on the 2955B, where you had to pay extra for the TX monitor. I will open up a 2955R in one of the videos and just have a look inside to see what's inside with regards to the sensitive receiver option. So yeah, it looks like everything's going okay. It looks like you know, we've got a working radio test set, although I am going to check the function now with the signal generator and the spectrum analyzer and other test instruments I've got here to verify that the level that's coming out and transmit level going in, for example, is working as well. So we'll see. That'll be the next part of the video. So yeah, but for those that haven't seen inside the 2955B before, stick around. I'll do a little walkthrough of the internals and what they do now, and you know, and obviously give you a bit of information as to all the functional side of it. So yeah, interesting. I've just got some feet to find for it now, which I've got in a box somewhere, and a carry handle, and then we can reassemble it all and put it back to how it should be. Back soon. Right, before we do any functional testing, I just wanted to have a quick walkthrough of the boards and the sort of functional description. We're on the underside of the unit at the moment. I've removed the screening cans that cover this entire tray. One of the most common faults that you'll find with quite a lot of the older 2955 models, the ones that were sort of produced in the early 80s, is, especially if you've had a lot of field use, the screws that hold the screening cans on the bottom here, which are these gigantic metal shields, they become loose with vibration of obviously being in a vehicle going from A to B and being lumped about on site, and decades of heating up and cooling down, you know, and extremes of temperature cause the screws to actually become loose on the screening cans, and that can lead to intermittent faults, because what you'll find is if there is microphony, like the screening cans aren't attached properly and they're making noise, mechanically induced noise on the electrical side with the frequency sensitive components. When you're doing a self-test, the general sign of that is that it'll fail intermittently, not all the time on every test. It'll just be every now and then it'll fail one of the tests, especially if you're touching it or tapping it or moving it at the time, or it's on a bench where there's a bit of vibration or something like that, somebody walking past while the test's being done, and then it'll fail. And it's quite common fault that with them. So it's my recommendation that you tighten up the screws on the screening cans. I've had lots of these test sets where the screws have been well loose, they're backed off at least half a turn, and you know, you can get a good nearly full turn on the screwdriver to tighten them back up again. They've been really loose, some of them. Not all, it happens from time to time. I suppose it depends what life instruments had prior to you getting it, but it's always worth doing that. I've not had any cases where any of these bolts, nuts on the screening cans of these oscillators become loose or anything like that, but might be worth just giving them a proper tighten up. If you are going to tighten any nuts up on these, use a proper ratchet, you know, ratchet driver. Don't be tempted to use a pair of pliers. Now, unfortunately, on this particular test set, somebody's been using a pair of pliers on the power supply section. There's a couple of nuts that hold the power supply heatsink that's in there down to the main chassis, and instead of using a proper driver like I've just shown you, they've actually used long nose pliers, and it's put score marks on the nut, and it's a bit of a, you know, a bit of a bodge doing that, and you know, so use the proper tools, tighten these posts up if they're loose on the boards as well, because they sometimes work loose as well with the screws. Just make sure everything's nice and snug, put it all back together, and it should be okay then if it's failing intermittently. Now, you know, obviously there are component failures, as you'll see in my other videos. There's a common fault with a capacitor going short circuit on a couple of boards, one on this board and another on the boards that slot in on the edge on the other side, which I'll show you shortly. So there are common faults on the older test sets. I think with this being a B model, I can see that the capacitors are not the same make and the different values. So I think Marconi must have been onto that at some stage and you know, replace the caps with different makes because of the problems they'll probably getting with them. But yeah, so just look out for that. Okay, so we'll get into it then. Before we have a look at the back again, we really need to do an introduction showing the top bit, which is where it all starts. So we'll just turn it over. Now, first of all, on the front here we've got the RF sockets, which are the input and outputs of the RF signal generator and TX monitor on the unit. And what happens is that actually comes into this module here, which is this heatsink module. Now if I just turn it over again on the other side, not the lightest of things, let's have a look. Right, so down there you'll notice that this module with a heatsink on there has got two RF coaxial cables connecting to it, one from the BNC on the front and one from the N-type. Well, that comes into this RF power attenuator, and this has basically got an RF power resistor in there. This attenuates the incoming signal from the transmitter to about minus 20 dBs of what was fed into it. Now that's necessary in order for the rest of the instrument to take measurements, because obviously the other boards on the instrument are quite sensitive and they can't take high RF power. So we have to attenuate that right down before it's taken out the back and sampled by the boards on the underside, which I'll show you shortly. But in addition to that, this RF attenuator module here, this is the step attenuator that has multiple relays in it and attenuator pads that switch in and switch out depending on what level you're entering on the front on the operation of the test set. So this will switch in and out various attenuators from the signal generator section for the receive testing, and in turn then it will output that via this solid coax that you can see here into this attenuator. Now this step attenuator can't take much RF power. It's very low powered rated as far as transmit RF's concerned going into it. So we couldn't just connect that directly to the N-type at the front. Obviously when we transmit into the unit it will burn this out. So what they do is they feed this into the other side of the 20 dB pad that's in here, the attenuator, and naturally any transmit signal coming in, like in duplex mode when we're transmitting and receiving at the same time, the actual transmit signal that's coming into there, it could be like 30 watts for example, it'll get reduced by 20 odd dBs, whatever it is, 30 dBs, whatever, and the signal level will be so low that any RF coming back into here will be dealt with by this load resistors that are in the attenuator section, and it won't cause any damage, you see. So you can stick as much power as you want in at the front there within its tolerance, and the signal will be too low coming here back to cause any damage to either the signal generator or the attenuator. Now likewise, when we're dealing with a receive signal going out, we're wanting to generate a signal to go through out to the front sockets, the signal generator has to take account of that attenuation. So say for example wanting 0 dBm coming out the front, and this is say a 30 dB attenuator, right, for example. what happens is then this has to produce 30 dBs above what the attenuation is here to compensate for it. So the RF signal generator is quite it's producing quite a lot of RF signal to get past this attenuation. Otherwise, you know, if this outputs 0 dBm from there, it'll be minus 20 dBm as it comes out of here to go to the front socket, because this will attenuate it. So how it works is that this is always, whatever the attenuation of this is, I can't remember off the top of my head exactly what the figure is, it's 20-30 dB, but it's quite a high attenuator level. It has to be that level again higher on the output here. So the way the instrument's set up, it takes into account the attenuation here and then inputs the appropriate signal level to make up for that difference before it leaves on the output. Now what sometimes happens is when people are stupid, and there are lots of stupid people in the world, believe me, I've met some exceptionally stupid people that do some very stupid things with RF test sets, and I've met people that have fed 400 watts up the you know, up the front there, up the jacksie, and it's popped the attenuator resistor that's in there and bolted to the heatsink. I mean, you can feed in more than 75 watts into this and it'll handle it quite well, you know, 100-150 watts momentarily, but the instrument's built to take 75 watts continuous. So, you know, if you start doing stupid things like feeding 400 watts of RF power up it, then, you know, you're asking for trouble. And you know, the attenuator resistor in there goes fizz bang, and then, you know, obviously it pops it, and so it affects both the transmit and receive side of the instrument when that happens. Now, you know, obviously if a resistor breaks down in such a manner where it can connect RF through it as part of its failure when it burns, it can also feed that amount of power into this attenuator module, and fizz bang, that'll go as well, plus other things beyond it. So, you know, it can cause a lot of damage. So never exceed the amount of RF power that's on the front unless you're a complete lunatic, in which case you deserve all you get. But this module also has a low power attenuator in as well for the 1 watt port, which is the BNC, and so much like the high powered port, it has a giant resistor on the high power port that, you know, obviously attenuates the signal. It has also a lower power rated attenuator for the 1 watt port, so that it allows the instrument to have greater sensitivity on the lower power ranges. And likewise the same applies when we're using the 1 watt port for the signal output. Then it takes the attenuation in here into account with regards to what signal level comes out the step attenuator to compensate for that. And so when we're doing repairs on this part of the instrument, the RF attenuator, it's important to pay particular attention to things like using the correct parts, not having excessive lead length, things like that, because it affects the RF performance of the instrument, and must make sure that that's, you know, whatever repairs are done in there is actually done properly. Obviously we've got the loudspeaker here, and going up the instrument inside we've got the CRT tube. Now the CRT tube is running from an EHT supply. I think it's about 10,000 volts on the anode cap that's on here. It's well protected to prevent you from getting electric shocks. It's quite well made. Now behind that this sort of can here, further down there's silver module that you can just about make out down there, and that's the reference oscillator. So that's the clock of the instrument. Now if I just turn it back over so that we can get a look at the right, so down there with the red circle on it, that's the TCXO crystal oven 10 meg reference oscillator. We've got obviously outputs from this fed off then to various parts of the instrument to give it its 10 meg reference. So the accuracy, the frequency accuracy of the instrument is set up using these potentiometers that are on the board that allow you then to adjust the accuracy of this. So that's how you calibrate its frequency accuracy. We've got the line output transformer, or the flyback transformer as it's commonly known as, which produces the EHT for the anode of the CRT, the cathode ray tube, and then we've got various parts of this circuit which is used then to obviously driver focus coils and horizontal and vertical scan coils, and these the pictures set up by these three potentiometers, which then allow you to adjust the picture horizontal and vertical alignment. Now these boards here are the main processing part of a unit. We've got the VDU board and microprocessor boards, which obviously deal with all the computer side of the instrument, and the graphics generator, or what's called the VDU, visual display unit board, which produces all the graphical content that you see on the, what we'll call in the modern terms, GUI, which is this what's displayed on the cathode ray tube. So all the video images that you see on the screen are all produced through one of these boards. The other board is a digital scope board, which deals with all the digital scope for audio input measurements and transmit monitor measurements, etc. And then obviously we've got another board here with all these pots that allow us to calibrate certain measurements that the unit can make. So this board here has quite a lot on it. It uses the it does the transmit power monitoring, it does the TX frequency mod readout from the modulation as well. It generates audio signals as well for the AF gen for both receiver testing, and there's also our AF gen out on the front down there on the BNCs. It does all kinds of things along with this board as well. So now if you look at my other video, which is a 2955A repairs, I think I'll go through what these boards do exactly, because each board has a multiple responsibility. Each board doesn't just do one function, it has several functions within the board. So there will be several parts of the instrument functions that will be on each PCB, not just, you know, responsible for doing one thing. So again, we had in one of the other repair videos, there's a capacitor on one of the supply rails on this board with the blue pots on that went short circuit. It just happens to be the same capacitor that went short circuit again on another repair video that we did, which was the same value and voltage and manufacture that was also on the underside board, which is a 200 megahertz oscillator. So that as well, you know, can be a problem with capacitors. The motherboard down there is just like any other motherboard you'll see in any other instrument, but there is actually, you'll see down there on the motherboard, there's an option where it says receiver interface, or this plug here, and that's where, if we have the optional TX monitor for monitoring off-air signals, which is basically a sensitive receiver option, then that will connect in there. So it looks like as if this instrument isn't fitted with that, even though it's got the button on the front for it. But yeah, so that's basically a little quick rundown. As I say, I can't give you too much detail because the video will go on forever regarding to, you know, what every single function these boards do, but none of these boards deal with any high frequencies. They all deal with intermediate frequencies in the low frequency range, in the HF, VHF range. So all the signal sampling and all the work that these do is all at low frequencies, because we convert the signal, as I'll go into next on the underside, down and down and down into a low frequency that these boards can deal with, to do TX monitoring, sampling and synthesis. So that's basically what they are. They do pull out. There's these little black lugs that pull and then the board comes out. So that's that. That's the GPIB board there, the general purpose interface bus board, which then connects down onto the motherboard and allows us then to use external test equipment, or ATE, automated test equipment, programs and software that can be run. Marconi did a piece of software many years ago called PMR Test, and basically it's a piece of software Marconi wrote where you can write your own scripts, and it'll put the test set onto whatever frequency you assign it to and measure certain levels, and it'll give a pass or a fail, so it looks for data coming back out to compare, and if the limits of audio or signal, or for example transmit power or mod, aren't right, then it'll pass or fail. And you can get a printout from that software as well, which is used in customer conformance testing, things like that. Also on the underside, so on the rear rather, we've got the power supply, which we've been dealing with in this repair, and the fan, the BNCs on the back, and all the supply connections and switching, etc. The power supplies on these tend to be quite reliable. There are one or two issues it can get with them. This repair that we've done on this is quite rare really, with the diodes blowing up. More often than not it's the transistors, the IRF 540s, switch mode transistors, that tend to fail more than anything really. So here we've got the main RF tray underneath again. Now this board here does all the signal generation. So this generates all the RF signals that the instrument will be used on, and it has three main oscillators. And how it works is that rather than using the very high frequencies above 500 megahertz or whatever, it doesn't use an oscillator that goes up that high. What it does, it uses low frequency oscillators, and then using these what look like to be printed circuit coils. I'll see if I can zoom in on one. These, it uses these in conjunction with pin diode switches and filtering to produce a bandpass filter, and it selects the first harmonic or the second harmonic from the oscillator. So to get the higher frequencies, that's what it does. It selects harmonics then to generate the right output signal across the usable range from 400 kilohertz to 1 gigahertz. And so that is the synthesizer, oscillator, the phase lock loop is all in there basically. This board here is one of the problematic boards that we had previously in one of the other repair videos. A couple of common things that occur on this. We have a 200 megahertz oscillator, which is in this area here, and this generates this is an independent oscillator that runs in its own right, and it's frequency locked by these chips here. This is a phase lock loop for that 200 megahertz oscillator, and we have a mixer here, and basically RF signal that's being generated below 88 megahertz. Say for example wanting to monitor a signal, a transmit signal coming in at I don't know, 88 megahertz, below that, or we want to generate a signal that's you know, for example we want to generate a receive signal to a radio, an RF gen signal below 80 megs. What it does is it uses the 200 megahertz oscillator, which is fixed frequency and it's free running, and it mixes with the incoming signal from here, which will be below 80 megs or whatever, to mix in this mixer, and then the IF output then will be between 400 kilohertz to I think it's 88 megahertz. And this is only switched on when we actually enter a frequency on the front, an RF gen frequency below 88 megahertz. So I'll just correct myself on what I said earlier when we were discussing this about it also being involved in the transmit side. It isn't. I was wrong in saying that. it's on the receive side when it's generating an RF signal out. Obviously when we're transmitting, then it's read by the frequency counter board, and then an IS fed off for the RF power, which I'll go into shortly. But yeah, so when we're generating a receive signal below 88 megahertz, it's actually a product of what's coming in here, which is below that frequency, mixed in with a 200 megahertz oscillator, which then produces the difference in IF, which is fed out to provide the frequency generation below 88 megahertz to down to 400 kilohertz. And one of the common failures that's on these is these OM345s, because all RF signals for all bands pass through this link here from the synthesizer board. They either get mixed with this oscillator, it's below 88 megs, or they get directly connected through bandpass filters, which are these inductors here, printed circuit board inductors, and pin diodes switch them in and out depending on what frequencies we're selecting, so that it filters off all the unwanted harmonics and distortion and allows that to pass through then for the amplification stage. And there are 2 or 3 stages of amplifiers. There's an RF attenuator as well, so it can switch its output level here before it gets to the step attenuator as well. But these OM345 modules are common failures. They were made by Mullard originally, and then Philips started producing them. And these are basically monolithic amplifiers on a thick film substrate, and they provide about 20 dB gain each, wideband from 400 kilohertz right up to 1 gigahertz. And they're like Victory V suites with legs coming out the bottom of them. That's the best I can describe them. If ever anybody's had a Victory V cough suite, that's basically what they're like. This is another version of it, another OM module, which again is manufactured by Philips, and that produces again a certain gain as well. So that then passes off through that chain then to the socket here, which then goes to the step attenuator, which we're looking at on the other side. So if I can get it to focus, because its camera's playing up again. That then, this relay has a certain switched attenuation, which you can switch in and out depending on what RF level we want to come out. So again, that's another form of RF attenuation, and then it's fed out up to that solid coax, which then goes to the step attenuator, which was what we looked at earlier in the video, that big module bolted on the side before the RF attenuator. So that's that board. So that's mainly the signal generator amplifier, local oscillator for frequencies below 88 megahertz, which then generates all the HF side or VHF low. We've looked at the synthesizer phase lock loop board. This board here is deals with the transmit side, so any signal coming in from the transmitter, which is via this solid coax, this goes to the RF power attenuator that's bolted to the side that we looked at earlier on. It comes in, it goes to an RF attenuator again, so when it's wanting to receive very low RF signals, it can switch minimum attenuation in to pick up the microwatts, milliwatt levels of signal. And obviously then if it starts taking a lot of power in, this will switch in a second pad to attenuate further. This is a frequency counter board, so this then gives an output via this data bus to the digital board, telling us exactly what the frequency is that's coming in. And then we've got part of that signal as well is branched off this way and goes to this board here. Now this board does two things. This board recovers the modulation content from the signal that's been fed in from the transmitter. So again, the transmit monitor, the transmit signal comes in through this pad, wires gets branched off, one to this board, the frequency counter, and then down here to this board. This deals with two things. It deals with all the modulation recovery from the RF signal that's coming in from a transmitter measurement. So it'll deal with FM demod, AM and phase mod demod, but as well as that it also deals with the transmit RF power, and how it reads the transmit RF power on this particular instrument is that it takes the IF signal, it down converts the signal basically that's coming through this feed through here, down converts it, which is why it's got this oscillator, and produces an IF, and one of which connectors here goes off to the rear, the BNCs on the rear of the instrument, which allows us then to feed obviously other instruments there, spectrum analyzer, etc., to monitor the IF output. But the IF that's detected here is then forwarded on as well with another coax to one of the boards on the top. If you remember, there was the vertical boards in that can. There was several vertical boards, and on there's an IC which takes the IF and reads the RF signal power from the IF, which then derives directly what the transmitter power is that's coming into the instrument. So it uses an IF down conversion process, and then it reads that signal level then to produce the actual transmit power output, as opposed to having which you'll find say on the Roden Swartz and HP Agilent test sets, they use like a high frequency Schottky diode on the RF attenuator pad to directly read the proportional DC signal that it will rectify from the RF, and then give an RF reading that way. But this does it differently. It does it through reading the IF signal and then looking at the power of the IF signal, detecting it, and then reading that out then on the display. So I think that's about it really. I don't think there's anything more to add on that. I think it's like so many things, you know, common failures, these thick film amplifiers, and caps going short and transistors blowing up, and tantalum capacitors as well sometimes go short on these. I've had a few of those. I used to work with a guy many years ago who used to draw smiley faces on them. If they tested out okay, he used to draw a smiley face, and then you know, the rest of them then. So he always used to say a working cap's a smiling cap. Anyway, just make sure that if you get one of these instruments that all the screws are all nipped up nice and tight on the boards and the screening cans when they're in place, and you shouldn't you know, start at that if it's failing intermittently on its self-test. So we'll whip the case back on, and then we'll start doing some functional testing to see whether it's actually reading correctly as well. Okay, now we're ready to do some calibration checks of the instrument now that it's been repaired. I thought we'd do the most difficult alignments first, or checks, to make sure that the RF signal generator from the Marconi 2955B is performing as it should. When you read the service manual of a 2955B, it details separate instruments that you can use to do certain performance tests, to check things like the mod, the RF signal generator, cyanide, all sorts of tests and measurements. So that's what we're going to look at now. Now, obviously the range of this test set, as far as the RF signal generator level is concerned, we've got quite a... I'll just disconnect this for a second so we're not overdriving something. Right, so we've got an RF level on the N-type. We can go down as far as neg 135 dBm, and as high as, keep going and going and going, minus 15 dBm. So that's on the N port there. So we're going from neg 135 dBm up to a higher level of minus 15 dBm. Now on the BNC port, we can go as high as plus 5 dBm, okay, and as low as, let's have a look, neg 115 dBm, you see. So we've got different levels that can be achieved depending on which port we choose. So one of the issues that we've got when we're calibrating something like a signal generator, it doesn't matter whether it's a radio test set or a separate signal generator on its own, RF signal generator is neg 135 as far as RF levels are concerned is right down here. Now that's dBm. Now most radio receivers like radio transceivers are quoted more or less 0.2 microvolts, or when we convert 0.2 microvolts into dBm, that would give us, for example, if I go on there just to show you how easy it is, 0.2 and then the microvolt key, which is that there, and then press dBm. So that's neg 127 dBm. So most radio transceivers around about here in RF level, a radio receiver would be quoted in the service manual or the spec for that radio transceiver. It would say that it would give 12 dB synad at neg say 120 dBm. So that's the point where the signal will be quite noisy and crackly on a radio receiver. In a radio transmitter receiver, like a handheld radio, a mobile radio, an amateur radio transceiver, a private mobile radio transceiver, a marine radio transceiver, an aircraft radio transceiver, whatever. They generally are roughly around that sort of between half a microvolt, 0.5 microvolt, down to about 0.2, 0.3 microvolts. Some really good radio transceivers can actually pull out signals quite well, even down to 0.1 of a microvolt. But you get to a stage where the squelch can lift because the noise that's coming from the atmosphere and from the solar system, for example, and the sun in particular, when you connect such a sensitive receiver to an antenna, the noise floor is actually quite high. And therefore it can open the mute on the receiver, and that can get quite annoying. So there's a limit to where you can go with receiving signals, but generally speaking we would use things like low noise amplifiers to pull out a weak signal from a level of noise. But it's just like, you know, what's the analogy I'm trying to find? It's a bit like you get to a stage where you're finding a needle in a haystack. You know, the signal's there, but the hay around it, or we will call that noise, drowns out the signal. So you can amplify and amplify and amplify and filter and clean up and do that as much as you want, and there comes a point where the noise itself, which is at the same frequency as the signal, becomes an obstruction to recovering that signal. And that's what we're going to look at next. So as far as RF levels are concerned, most radio receivers generally operate in sort of this range. So if that's minus 135 dBm, that'll be minus 127, and then 0.5 microvolts, which is generally when a receiver between 0.5 and 1 microvolts would receive a signal very well with very little noise, and you'll be able to hear the content, the modulation content, without actually having too much of a problem understanding it or hearing it. And that will be neg 119 dBm. So that neg 119 dBm. Now that there is where most radio receivers in the world, don't matter who makes them, manufactures them, generally they receive a signal within that sort of range. So the signal will be most quieted, if you like, or with very little interference or crackle or pop or noise at this point here, and would be very weak and very unintelligible or difficult to distinguish the noise from the signal at this level here. Now obviously radio receivers can receive signals much higher up as well, and the stronger the signal, obviously the less noise interference or distortion there will be. And there comes a point in all receivers where if a signal's too much, there's an ALC, an automatic limiter control, which will prevent the receiver from being overloaded. So again, that's where we can go right up effectively off the page, really, as to the level that the radio test set can produce. But I've drawn it here just to give you some scale, but in actual fact, the level of signal that a radio test set can use will be like looking at a cigarette packet at the side of Mount Everest. So if you can consider the level of signal that the test set can produce at its maximum, it will be equivalent to, you know, Mount Everest in height, in amplitude, whereas the lowest signal level that it can produce will be equivalent to a cigarette packet in comparison to the enormous size of Mount Everest. And so the RF signal range ability of a radio receiver to receive an RF signal will be equivalent to, from a very high level where you've got a transmitter and a receiver in quite close geographical proximity, to something where we're receiving a signal perhaps from the other side of the world or from a very distant transmitter where the signal level's very low. Now most measurement instruments, and I'll demonstrate that later as well, this noise level here, where we can go right from receiving no noise at all right the way down the RF levels to where it starts to get noisy, and then we can still hear the signal quite well, and then suddenly it starts to drop off rather quickly, and then we get very low signal level with very increased noise and crackle and distortion, and then it disappears altogether. Now the issues that we've got in calibrating radio test instruments is that instruments such as a spectrum analyzer, for example, can make measurements normally down to about neg 100 dBm, and that's where this noise level is here in the noise. So when we get to neg 100 dBs down from whatever signal we're measuring in level, so we'll put neg 100 dBm in here, for example, and we'll have a look at that in a moment. What happens is that there comes a point around about neg 100 where it disappears the signal into this noise floor here, and there's sod all you can do about that really when it comes to measuring that on a spectrum analyzer directly. So then we have to use things, for example, like external low noise amplifiers to pull that signal out. Now if we get down to neg 100 dBs, we can calibrate the RF levels from minus 15 dBm, which is a very high signal level, sort of Mount Everest in proportion. We could turn the signal right down until we get to neg 100 dBm, and that signal will come right the way down almost into this noise floor. Now if we carry on turning this signal down beyond neg 100 dBm to say neg 120 dBm, this will not be able to measure that below neg 100. It will just sort of bottom out at neg 100 dBm and finish there. So we're sort of lowering the RF power right the way down till we get to about neg 100 dBm, which is around about here, I'd say, somewhere between there and there, and that would mean that that's the limits of our test equipment in itself being able to measure that kind of thing in case of this spectrum analyzer. Now we have other test instruments as well that we can measure accuracy. The spectrum analyzer is quite accurate down to about neg 100 dBm, and it can be used if a spectrum analyzer has been calibrated properly and what have you. But another instrument that's widely used and has a greater frequency range, right up to microwave frequency, in this case up to 46 gigahertz, is the 8920 series radio test sets. Sorry, the 6200 radio test sets, and these go up to around about 46 gigahertz in this case. Now, the vector network analyzers, scalar network analyzers that these are, have RF power probes, sensors, and that's what these are. They also use scalar detectors, but we're not using those to measure RF power. We use actual power heads, and that's what these do. And these are specifically calibrated across their entire operational frequency range from 10 megahertz to 20 gigahertz. So these instruments come into their own, they have their own speciality. Now, we use these instruments sometimes, as we'll demonstrate with this as well, to measure RF power accurately. These instruments are extremely accurate. They are very finely calibrated. These are aerospace, defence, research grade instruments. So the level of accuracy on this kind of an instrument is far greater than the level of accuracy on, say, a standard spectrum analyzer. Now, I'm not saying this isn't good enough to do the calibration, it certainly is, but for connoisseurs of calibration, the calibration houses that you send your test gear off to, like HP Agilent, Aeroflex, whatever, use instruments like this to calibrate most of the signal generator output levels, and then we'll show you what else they use as well in order to be able to pull out the signals and verification of levels. So these sensors though do have their limits, insofar as they can only go down in RF level to about, in this case, this particular one can go down to about neg 35 dBm, which is about here on this diagram. Now, that's okay, so we can measure from plus 33 dBm, which will be way off the page, right the way down to neg 35 dBm, and most signal generators are calibrated at neg 10 dBm. So as far as these are concerned, these are quite good for measuring that sort of power range, highly accurate, and therefore you can generally do most of your calibration accuracy between neg 35 and plus 33 dBm, which is about, roughly, you'd use those for that accuracy. So that's a good starting point, and is generally what our signal generators are calibrated to. Then you can get other sensor heads as well, power sensor heads that are more sensitive. This is one, and in order to use this with that analyzer, we have to use a 30 dB attenuator to calibrate it. So this has a 30 dBs more sensitivity than that one does at the back. Now, this allows us now, when we're using this type of sensor, power sensor, it has an extra 30 dB sensitivity. This will go down then to around about minus 60 dBm. Now, that allows us then to measure further accuracy down to this level of the RF attenuator section of the signal generator. So this doesn't have as high a power level measurement capability as this one does. So again, when we're measuring the higher levels of signal, that's not suitable. This tends to have an upper limit of neg 20 dBm, which is around about there. So if we go above minus 20 dBm, then we get an overload message coming up on the screen, and you can damage the sensor. So we use different power sensors, and indeed there are other sensors which do go down further, but not much further, to be quite honest, insofar as this instrument's concerned. So the lowest we can go to on the vector network analyzer is about neg 60 dBm for RF power measurements. Beyond that, then we start to use other instruments such as a spectrum analyzer, you know, for the more sensitive measurements. Now, obviously, radio receivers are generally capable of losing the signal roughly in this limit here, which is between 0.2 microvolt to 0.5 or 1 microvolt. That's generally the threshold where nearly every radio receiver in the world will generally lose its signal somewhere in between there. But as you can see, we've got this other part here which we can't seem to, you know, take any measurements of. If the lowest we can go with a spectrum analyzer is neg 100 on its own, that generally, this area here is the sort of measurement limit. So say for example that's 0 dBm, just for argument's sake. We can only go down to as low as, you know, neg 100 dBm, and that's it. You know, no matter what instrument you use, spectrum analyzer, you'll not be able to get beyond that, and that's where you know the buck stops. Now then, how Hewlett-Packard do it at their calibration house, as well as other calibrators, is they use low noise amplifiers. So I've just got an example here set up. This is a Marconi accessory, and it also houses a 20 dB RF amplifier, and this has got a frequency range of 1 to 400 megahertz, and it's at gain, as it says there, of 20 dBs. So what we could use is a low noise amplifier which connects between the output of the instrument and, say, the spectrum analyzer, or indeed the vector network analyzer as well, and we can then amplify the RF signal leaving here then to obviously be measured. Now obviously there comes a point where we've got if we're introducing, say, a 20 dB gain onto this, we can go down to neg 120. So with the amplifier we can roughly come down to about here. So that's with the amp. Because if we're injecting neg 100 dBm as a lowest level, which the signal generator can produce for the spectrum analyzer to pull out, then by introducing another 20 dB amplifier, we can effectively read down to neg 120 dBm. Now that means then, of course, we've still got a gap between neg 120 dBm and neg 135 dBm. So this is still an area that we're not able to look at currently. So what we could do is we could choose an amplifier that's got higher gain. We could choose an amplifier as well that's daisy chained to another amplifier. But then what you've got there, if you use multiple amplifiers, is that you have a noise figure. Now fortunately in this day and age there's actually quite a good amount of technology now available, which didn't used to be available years ago, because a lot of these devices were GASFETs or bipolar devices which have a lot of noise. So you know, you could have a 20 dB amplifier and it will give a 4 dB of noise. Now if it's producing 4 dBs of noise, then that has to be factored in the measurement. So for every time we introduce an amplifier stage, we then increase the noise level. So then we could have a total, in this case, of 8 dB noise. Now if that's the case, then we're getting more complex issues. We might have a 40 dB total gain across the amplifier from the input to the out, but we've also got 8 dBs of noise in that case to take care of. So modern day amplifiers like LD MOS amplifiers, the latest generation of monolithic microwave integrated circuits, or MMICs as they're called, they have a substantially lower noise figure, some as low as 0.5 dB now, and they're readily available from companies like Mini Circuits and other popular distributors. and you can get high gains, low gains, whatever, and generally they will be quite well calibrated and have a very wide frequency range. So you might get something that from basically go from 0 to say 3 gigahertz, and it'll have say a 30 dB gain. So that then would give us the capability to bridge this gap, this final leg, if you like, from there down to the neg 135 dBm, and that's where we can use then that amplifier in conjunction with a vector network analyzer or a spectrum analyzer to pull out, and we can use then the delta marker, which I'm going to be showing you very shortly, in order to pull that information out as to the level, so we can calibrate the instrument. Now, generally speaking, on most radio test instruments, if you calibrate it successfully between, say, plus 15 dBm and minus 40 dBm, for example, if its accuracy is okay across that level range, I would say from experience that it will be unlikely that the levels below that would be inaccurate, and it's for several reasons that will be the case. But for the context of this video, generally speaking, most instruments that are used to calibrate these kind of instruments are generally out of reach of the most normal sort of hobbyist, or radio amateur, or somebody who's interested in RF. When we start looking at calibration houses, they use some very fancy kit that's highly expensive, generally out of the reach of most people's capabilities to purchase due to cost, and they also have access to a lot of low noise amplifiers that are extremely high gain at very low noise figures over a very wide frequency range, and they are often used in these capabilities to measure those signals. So, you know, again, you can get them, but it's knowing how to use them, and it's important as well to notice or distinguish between a low noise amplifier, or what's called a small signal amplifier, and an RF power amplifier. You know, so I have, for example, what's used in transmitter RF power calibration. We have a calibrated RF amplifier here that's used for calibrating instruments, or also for research purposes, and this is manufactured by Calmus Engineering International. Now this has, for example, a 6 watts RF power range, but it has a frequency range. It works at 20 volts, 28 volts, it draws 1.5 amps, and it's got a frequency range of 500 kilohertz to 1 gigahertz or 1000 megahertz. Now this particular amplifier, the technology is LDMOS in this particular case, and it's an extremely wide banded amplifier that allows us to give a given input on a particular frequency range with a given output. Now, you would never use that kind of an amplifier in a small signal application such as a receive signal generator, simply because this is for RF power amplification, not small signal amplification. The level of output that comes out of the RF gen is too low for this to work, and it's rather deaf and insensitive, if you were to put it that way, in comparison to a small signal amplifier. A small signal amplifier is designed to take the smallest RF signal from the radio spectrum in microvolts power level and amplify it up maybe 20 dBs or whatever dB rating the amplifier is, but yet it's incapable of producing high RF power, insofar as might be able to go up to maybe 100 milliwatts in total power when it's saturated, but it certainly wouldn't be able to do any more than that. Now that's very important in this context, because this amplifier here isn't capable of amplifying very small signals. You need a lot of RF coming in, power. Might need to drive it with, say, half a watt, 500 milliwatts to a watt. Well, that's enormous, you know. Insofar as RF level's concerned, when we look at this diagram here, to drive an RF amplifier with 500 milliwatts, that would be equivalent in distance from the Earth to the Moon, in RF level, in height, in amplitude. So this is used for calibrating transmitter measurements, because it's a power amplifier. That's a small signal amplifier. Now, if this were to produce high RF levels, say 2 watts out of it, for example, which it wouldn't, but say if it did when it was saturated, then that's a problem, because it could damage instruments such as the radio test set down there that's only got 500 milliwatts on the BNC port. So it could blow that. It could also blow this, because this can only take 1 watt up the RF port. So this is where you've got to be really careful when using amplifiers, that you don't use power amplifiers in the case of measuring signal generators, because they can, if you know, you'll get to a point where you get it right up higher, the RF level, and some amplifiers can just take off between 0 dBm to say plus 20 dBm, and they can produce a couple of watts at that. RF amplifiers, power amps. So you've got to be very careful that you use the right amplifier, otherwise you can cause damage to instruments. And besides, we're using a low noise amplifier, which has been designed to take the smallest RF signals, the levels of such that you would receive on an antenna, an external antenna for example, and amplify them up. So in this capacity, what we're going to do now is, if I, for example, demonstrate that by connecting the spectrum analyzer now directly to the signal generator, we can now measure the signal directly that's coming out of the signal generator on the spectrum analyzer. So if we start at minus 15 dBm for example, okay, now we've got an RF level coming in. Now I can, for example, just have a look at this amplitude, just get it into just below the top line. We can already see now that we're starting to receive an RF level. Now the marker is at minus 14.23 dBm, and we're saying on there that we're giving out minus 15, so that's well within a dB accuracy. And we've got to factor in the cable losses as well, that you know, we're using special cable here. We're using aerospace grade cables that are extremely low loss, right up to microwave frequency. So even though we're using a test frequency of 300 megahertz at minus 15 dBm, we are actually you know, getting minimal attenuation. So that is the correct level there. Now I can go to markers, and the marker levels read incorrectly. Now as I adjust this down, say if I gradually adjust it to minus 17 dBm for example, I will receiving that minus 16.4, and then we keep going down for example, so that's, say we get it to minus 20 dBm, and now we're getting minus 20, yeah, more or less. So we're not getting any wild discrepancies, that's the point I'm trying to make. So I can keep going down now. So on the Marconi it's reading minus 30 dBm, and it still keeps going, and that's minus 40 dBm now, and then we get down to minus 50 dBm, that's minus 50, and then we can keep going down to minus 60, This is minus 70 coming up. And you're starting to see now that we're getting near the noise floor. So even if I pick up the amplitude now to make the spectrum analyzer more sensitive, we're not going to be able to do that, because obviously the noise floor starts to being picked up at about there, at about that level. So we're not going to be able to make this, you know, increased in amplitude, because the noises, we're almost down into the noise level now. We've still got a long way to go though, as you can see, if we can go down to minus -135 dBm. So now we're getting down to minus 80 dBm. And again, if we go to markers, have a look, we're minus 80 there. And if we keep going down now, minus 90 dBm. Reading that's okay, but now if you notice we're right into the noise now, and we're getting a bit of a dithering measurement. When you look there, it's dithering about, so we're already into the noise. Now I can go down to, I think it's about -100 dBm most, but even then we're well into the noise now, so that's -100 dBm. Now if I remove the RF signal altogether, now the RF signal is removed, that's as low as we can go, so we're not actually measuring anything now. At -100 dBm, that's it. We've hit rock bottom. We've hit the, you know, we've hit the noise floor down there, and we ain't getting out of that. So now where we're at is we now have to bring in amplifiers to amplify that signal. So I'll leave that at -100 dBm, and what we'll do now is we'll disconnect this this cable, which is coming out the signal generator, and we'll put that then onto the input of the where am I? Got my leads all mixed up. Alright, we'll leave that on there a second. And what we'll do, we'll just move the plugs. So this connects to the output of the amplifier. This connects to the input, and then basically we'll connect this when we can get it moving. Always a pain, these SMAs. So we'll connect that there. And then what we'll do, we'll right, put that onto there. So we're now coupling the signal generator to the RF input of the RF amplifier module, which is that Marconi accessory that's sat underneath. And I'm having some difficulties at the moment while I'm trying to work one-handed with the camera, just trying to get these SMAs to go on, which is, there we are, we've got it now, going on. Nightmare jobs, right, and that there. So we've now introduced a 20 dB amplifier. As you can see there, the signal is now distinguishable. So after that long-winded connection job, now we can get back to making some measurements. So now we've got says there -100 dBm, and you know, we've got -80 nearly dBm, so we've got the rated 20 dB gain there. So obviously now we can keep going down. So that box has given us a 20 dB advantage on previous. So I can probably go down to neg 120 dBm now before that disappears into the floor. So that's neg 110 dBm now, and so that's given us an extra 20 dBs on top. So that's neg 90 dBm, and then neg 120 dBm is probably where it'll floor out now, because it will be in the noise floor. So there we are. So that's effectively, if I put it at neg 115 dBm, we're starting to just resolve a small amount of signal. It's still in the noise floor, neg 110 dBm. There. So we can see it just peaking above the noise floor now. So we can really get down to roughly about, you know, neg 110 dBms. We can still see the signal. So, you know, beyond that we would need to introduce another amplifier. So on the diagram we've got down to about we said that 0.2 microvolts is neg 127 dBm. We have neg 120 dBm right down here. So for example, it's just a little bit above, sort of in this range here. We're getting down to about here now. So we've managed to get right the way down to this level, neg 120 dBm. So in microvolt terms it's actually a very low level, but we've still got this little bit to bridge here. If we want to measure the accuracy, they attenuate right down to its neg 135 dBm. So if we were to put a 30 dB amplifier on the back of the 20 dBs amps that we're currently using, so we attach another one, if you like, to give 40 dBs for example, then we should be able to resolve the signal right down to neg 135. Now that all depends on the sensitivity of the RF amplifier that we're using, and this is what causes them to be very expensive, because some amplifiers are not very sensitive with regard to what they're designed to amplify, you know, even if a small signal amplifier. So it's important that when we're selecting a low noise amplifier, an LNA, that it has the input sensitivity as well. So it might not, for example, start to amplify signals that are below, say, neg 120 dBm. Anything below neg 120 dBm, it may not be capable of amplifying that, whereas some amplifiers can. So it all depends on the design, and hence, as well as that, their operational capabilities, which equal cost. So it all depends on where we go with it. You can make your own amplifiers, obviously. You can buy monolithic microwave integrated circuits and build your own amplifiers as well. You can do that, but you know, if you're buying an amplifier that can go right down to very low signal levels, then they can become very expensive. So that's a little rundown on that. So I'll come back now in regards to modulation measurements. Okay, now we've connected the scalar network analyzer, which we can see on the screen there, which is an expansion of what the instrument shows. We've connected the power head to the signal generator output, and generally that's what these are used for highly accurate level measurements. And once you get the upper levels correct that we were discussing earlier, then generally the lower levels follow in line. But obviously with this head connected, I'm inputting a signal here at minus 20 dBm, which is there where it says level highlighted, and now we can look at the level that's coming out on the scalar network analyzer, which is minus 19.79 dBm. Now the error factor that it gives in the manual I think is 1 dB, so that's well within range at 1 dB. So that information you can see on the screen there is actually what the signal generator is giving out. Because we're reading that directly from the port, there's no cables or anything to take into consideration. This isn't a frequency cable, it doesn't deal with RF frequencies. This is a cable that has analog or digital levels on it. All the RF processing is done in this head here. So this is where the accuracy comes in. That gives absolute accuracy because this is a calibrated instrument and the head's calibrated. So this is exactly what the test set will be giving out. Now if I reduce the RF level now on the test set, we can get to around about -50 dBm on this. So for example, if I enter minus 40 dBm, then that level's given there, and I can keep going down to around about, that's minus 47 dBm. It's catching up, and we're getting now to the point where the bar graph will start to go down, where it's reaching its absolute limits. So if I enter minus 50 dBm, then it'll start to catch up, and eventually it'll read down to about minus 50 dBm after it's settled for some time. But again, you get the picture. You can get calibration of highly accurate levels right the way down to minus 50 dBm roughly. I'll enter minus 55 dBm, and we'll see whether it can resolve that. And it's slowly catching up, but again it's right at the edge of its limit now for the RF level. So again, this is where we're looking at the diagram here, which shows that we're getting down to around about this level, but we've still got all that way to go, which is a massive distance. It's like halfway down Mount Everest in amplitude in comparison to these lower signals here. So this is where we're getting down to there, roughly about minus 55, minus 60 dB. So then we need to introduce we can then at this stage introduce amplifiers in line with this. So again, that's where we can complicate matters as far as calibration, because we then need to take account in the measurement of noise figures, the dB noise that the amplifier would produce as part of its operation. We would need to know its precise frequency characteristics over the frequency range of the amplifier. So if we're going from DC to 1 gigahertz, we would have to know that linearity data. So obviously we can take that into account, and we could use that in conjunction with these power heads then to give that 20-40 dB extra signal level into this kind of a sensor. So whereas a spectrum analyzer would see the noise floor, and obviously the measurement would disappear into the noise at some point, these don't tend to have a noise floor issues, because these measure radio frequency power directly, but naturally they aren't that sensitive that they can measure right down to neg 135 dBm. So at some point you can amplify and amplify and amplify, but then you're introducing more and more noise, more and more trouble if you like, and that can then influence the measurement. So this is where we need to be careful of what amplifiers we select for the role, and what kind of amplifiers they are, what the noise figure is, and the gain and linearity across the entire frequency range. This is rated 1 to 400 megahertz, but it would be no good at using this, say, at 800-900 megahertz or 1 gigahertz, which is the upper limit of this instrument, because its gain wouldn't be 20 dBs. It would probably fall off quite sharply above 400 megahertz. So Again, you need to select the correct amplifier for the job. But you can see there we're measuring quite successfully now that it's settled neg 54 dBm. And again, due to the sensitivity of these probes, when the ambient temperature changes, then you need to zero the detector and basically you know, redo your measurements. So that's how accurate these instruments are, these vector network analyzers, that the probes themselves need regular calibrating on the VNA so that they're reading perfect accuracy. So that kind of accuracy there is about as stable as you can get when it comes to calibration. They are the bee's knees as far as, you know, calibrating RF levels. But then for the next portion of signal, right down to neg 135, then we could use the delta markers to make comparisons with the RF levels, what they were at the start, and then we could keep reducing and reducing the RF level until it reads down to the minimum with the amplification in. So it's a combination of using the delta markers and the low noise amplifiers, and again, you can make those comparisons then as you're going down. And it's very intense is doing calibration because there's so many factors to consider, and it can become quite tiresome. So, you know, we can, in this capacity for example, we can make a comparison. So we're at neg 55 dBm for example, which is coming out the test set. We're amplifying it by 20 dBs, so we're getting neg 35 dBm roughly. We can for example go to markers, delta marker, and then basically from here we can then reduce the RF level, and as the RF level comes down, then we get the dB difference between the current level and where it started off. So that's neg 100 dBm. So that can give us the level. Once it gets right into the noise floor again, then, you know, the basics of that measurement though is just to say, well, that's my starting point. If a manual says, for example, do your calibration at neg 10 dBm, you'd start at neg 10 dBm, which would be the delta marker starting point. Then you would reduce the RF level on the test instrument then to whatever it says in the manual, reduce it to in 1 dB steps at this particular frequency from neg 10 dBm to neg 50 dBm, and then you would be able to see the 1 dB steps all in calibration from the start point to the end point as it directs you in the maintenance manual. And so that's how you would use that in that capacity. But again, it's more to do with accuracy than it is to do with you know, recording the level out of here. You obviously got attenuation in cables that you have to factor in. You can sweep these cables separately on the vector network analyzer to give you the dB levels of loss across the entire frequency range from, say, DC to 1 gigahertz, and then once you know what the losses are in the cable across that frequency range, you can take that into consideration as part of your measurement because it affects the overall accuracy. Now, in calibrating the instrument, if you do find the levels wrong, there is in the service manual a mode, a secret mode, calibration mode, which is when it's powered on, there's a sequence of keys that you press in a particular order, and then what happens is it puts it into a calibration mode on the screen, and I'll go into that next if I can find that part in the manual. I'll show that as part of this calibration video, but it basically will calibrate put the calibration menu up, and there's hexadecimal values then that finally adjust the pin diode attenuators internally for the 1 dB steps across the frequency range of the instrument, and then it stores that DAC value, that digital analog conversion value, in its memory, so that when you recall that frequency in that level, it will then produce the right output level. So that's a little rundown of RF levels. So now let's have a look at the calibration further beyond that now, which is to do with modulation and making sure that the signal generator is producing the right mod levels. Okay, now we're ready to do the modulation tests. We've just connected that up to the HP8920 Spectrum radio test set, and just move that light out the way a little bit more. Now, interestingly enough, the radio test set allows us to demodulate the signal and hear it on the speaker, but at the moment we've got the spectrum analyzer in the off-air monitor mode. Now as I reduce the sort of noise level, so again the squelch opens on the radio test set about there, which in microvolt terms is 1.6 microvolt. So if we, though it's not part of this measurement we're going to be doing, if I put the mod on, set mod, and you can see there that the signal's quite noisy, and obviously it gets worse as the RF level goes down till it squelches out, and then there. So this is what we were talking about earlier with radio receivers, that they have a level that they go down to, and then suddenly then things start to fall off rather rapidly. So we come right the way down the RF levels, and the signal just then starts to get ever so noisy, and then suddenly between these sort of limits we go from a signal that's sort of that quality, where there's a little bit of crackle on it, but you can still, you know, distinguish what's been conveyed on the signal in modulation. So if that was speech, you'd still be able to hear somebody talking quite clearly, and then just a little further down then we lose it altogether. So it's quite a narrow little window that we're dealing with. So you can see there, it's starting to get noisier, and then it's gone. You know, you can't hear that. But likewise, as we increase the signal, you know, again like a radio receiver, you can put quite a large signal in, and it'll cope with quite a large signal going right down to a very small signal. You know, I mean, there we're at 680 times higher in level than we were prior. We're reading 684 microvolts. So again, this is a Mount Everest scenario that I was talking about. You know, that's 1 millivolt, 1000 millivolts, 1000 microvolts is 1 millivolt. So, you know, now we're going down, we're in hundreds of microvolts, 400, 300, 200, and we're still being able to demodulate the signal. And then we're going right the way down to 60, 40, 30, 20. We can still hear it pretty well, and then it starts to get noisy now at 9 microvolts, and then you can see it falls off rather rapidly. So basically that measurement, you know, between sort of on this scale, 9 microvolts is way down here, and then we were, as you saw earlier, you know, we had at one point, you know, with the signal having no noise at all, you know, we were right up here at 600 odd microvolts, way off the end of this page, you know, disappearing off out the window into 3 miles away down the road, in comparison to what we've got down here. You know, we had 1000 microvolts, and the receiver was still working properly and we came all the way down, miles and miles and miles away, until we entered this room we're in now, and we started at the end of this page. We carried on down here, right the way down. The signal was fantastic, could still receive it, and then when we got to like 9 microvolts, that's when it actually started to get noisy. So this is, again, that's that analogy I used earlier, the Mount Everest versus the cigarette packet in amplitude of signals, because obviously the signals that are coming out the air are in the microvolt region. They're very low down, you know. Doesn't matter how much power you transmit off an antenna and stick out into the atmosphere, you know, once it leaves that antenna, even if you're 300 yards away from that area, you could be broadcasting into 1,000,000 watts of RF power. The fact is that less than a few hundred yards, few hundred meters away from the antenna, your signal level that you've got to pull out the air is only in the order of microvolts to perhaps maybe a millivolt if it's extremely close to a transmitter. Obviously, if you get you know, another 100 meters beyond that, another 100 meters, then you're definitely into the microvolt range. So you can stick as much juice up that antenna as you want as a transmitter, but at the end of the day, the power is vastly reduced once it enters the atmosphere. The losses that in the Earth's atmosphere are enormous, and so that's why radio receivers need to be able to pull out signals that are in the order of microvolts, you know, hundreds and hundreds of thousands of times smaller than the RF signal is that leaves the antenna in the form of a transmission. And that perfectly demonstrates it there as well. But again, you know, you've got this issue where if a receiver's deaf because it's got a fault on it and the amplifier in the front end, the low noise amplifier like we've got here, isn't functioning properly, then it won't be able to receive the signals properly off air from an external antenna. So that's another fault kind of thing, which, you know, I went into in the CB radio tuning video. If you look at that, you'll get a good idea as to how we increase the sensitivity of a receiver and align a receiver so that it achieves its optimum performance in order to discriminate and demodulate an RF signal that it's designed to receive. So we can hear the 1K tone quite nicely there. We'll measure the RF level, the AF level, or the mod. So we can go to transmit, and we can see that the FM deviation on the mod meter, it says, is we'll just put a minus 15 dBm in, so that it's getting a saturated RF level. Now it says on there we're giving 10 kilohertz, 1 kilohertz tone at 10 kilohertz deviation. We're using FM, frequency modulation, and again we can see that quite clearly on there. So let's have a look here, and it says there that we're doing 10 kilohertz deviation, 10.65. So if I do set mod level 5 kilohertz on the Marconi, then we reduced it to 5 kilohertz. So we can see that the AF frequency is 1 kilohertz as well, at 9999 whatever. So its frequency accuracy and its FM deviations correct. So we can move on to other measurements. We've also got the TX frequency as well, so we can check the frequency accuracy of the instrument. So normally to check the frequency accuracy of the instrument is you would, for example, the instrument you're making the measurement from, which is the Marconi, this, you wouldn't lock that to a frequency standard externally. It will be on its own internal, as it is now, standalone clock, oven crystal controlled frequency standard that's within it. You would lock that to an external reference, so whether that's a rubidium standard, an atomic frequency standard, an off-air frequency standard, whatever, you would lock that to a GPS frequency standard, etc. An external source that's calibrated that you know is accurate. That would mean that instrument's bang on frequency then. and it wouldn't be using its own internal reference, which it has as well, but you would lock it to an external source that's a calibrated, known, accurate frequency reference source. So that's spot on, that's as accurate as you can get. You will then connect this instrument to that. You will then set the signal generator up to provide a frequency, given frequency and a level, which the manual would tell you what that level should be, but generally it would normally be 0 dBm into that instrument, and then you would then be able to check the frequency. If the frequency is off a long way beyond the spec that's quoted in the manual, then you would whip the lid off, or you would do the adjustment. Some modern test sets are done through software adjustments, others, like the older ones like this, are done with your manually tuning a potentiometer inside or a capacitor in order to bring the frequency accuracy on there, and that's what you would do. Now you may wish to use a very high accuracy frequency counter for that, because obviously these instruments all have accuracy and tolerances that differ in the specification. So again, the Marconi vector network analyzers here have a frequency counter built into them that's, I think it's 12 or 16 digits, so that gives one of the highest accuracies that you can have. It's a microwave frequency counter as well, so they tend to have a higher stability and higher accuracy than a standard signal frequency counter that can, say, go up to 1 gigahertz. Because they're highly accurate, that would mean that your accuracy is more assured with those than it would be with, say, a radio test set. Not that that isn't capable of doing it, but that's just, you know, the differences between the instruments. So that proves that the FM modulation's working fine. So now we'll have a look at the AM mod. Okay, now we've got the AM set up. We've got 60% modulation for this particular measurement, and as you can see on the Hewlett-Packard radio test set, the AM depth is at 60%, the 1K tone still there, and the frequency accuracy is still there, and we can hear that on the analyzer as well. So that proves the AM side of the radio test set is functioning as far as the signal generator is concerned. There is phase modulation as well. If we had the phase detector on the instrument as well, then we would be able to you know, check the phase mod as well. So that's just a little rundown on that. The next test I'm going to do is the AF gen, because obviously we can generate a signal coming out these ports. Then we'll do the transmitter tests, and we'll have a look at some other checks as well that we can do. Okay, so this test is to look at the accuracy of the scope and the bar charts. We've got in the RX test mode, normally in for example receiver testing, we will generate an RF signal out of the ports here, the RF ports, to a receiver. The audio content that's been demodulated from the RF carrier will then be passed back into the AF input on the analyzer, so that we can measure the signal to noise and distortion, and the AF content that's coming out the radio receiver to do alignments. So that's what this test looks at now. So we've set up the radio test set over there on the AF gen, so we're giving out a particular level. We've got 50 millivolts at 1 kilohertz, which is what's in the AF Gen 1 settings. I know it's not very clear on the video due to the screen size, but basically we can test the filters here as well, because we can put frequencies in that the filters can't can reject as well, and the bandpass filters. So at the moment we've got a 300 Hz to 3.4 kHz filter in, so the 1K frequency that we're reading here is within that filter range. We're reading a voltage here, AF volts at 51 millivolt. The other test set's giving out 50 millivolts, so that's quite accurate. We can have a look now with the scope, and we can then adjust the range appropriately so that we can read that out on the scope and set the position up as well. Now what you can do on this is when you set the scope up, you set it up so that the center line is on the center graticule of the screen, and then you can then look at the AF signal, check that's there. You can then increase the AF signal on the instrument, the source instrument as well. So for example, I could put in I could increase that proportionately, so that's 140 millivolts, and again it's keeping track of it. If we keep going, we can get right way. That's 310 millivolts. It says it's getting 317. And then we can go right the way up to, what is 1 volt, for example. We'll try and get it up to 1 volt. So that's 1 volt, 1000 millivolts. That's reading correctly as well. So that's how we can check the AF. We've got a volume, so we can listen to the audio as well. So the frequencies are correct, the level's correct, and then of course we can increase the frequency as well if we want to, the source instrument, so we can check its accuracy over a given audio frequency range, and so that's generally what we would do next in the other steps. Right, now we're on to transmitter testing, and what we've done, we've set up the HP8920 over there to give 0 dBm output at 300 megahertz with a 3 kilohertz tone, a 3 kilohertz modulation with the 1 kilohertz tone for deviation in FM frequency modulation. So 0 dBm in power is equivalent to 1 milliwatt. Well, we're connecting this now onto the low power port, which measures up to 1 watt, which is 1 watt maximum. And what we're doing there is we're looking at the RF power here. It's obviously reading just shy of 1 milliwatt, 0.94 milliwatt. I think the spec in the manual is like 0.5 of a dB or 1 dB, so that's well within the tolerance. We've got a level, a modulation level and frequency displayed here. We've also got the 15 kilohertz low pass filter on. So what I'm going to do for further accuracy is I'm going to select the bandpass filter here, so we can have a look at the speech band, because we've got basically a 15 kilohertz low pass filter, a 300 hertz low pass filter that's for CTCSS, and then obviously we've got the 300 hertz to 3.4 kilohertz. So that allows us to pull out the 1K tone properly. So we're receiving a 1 kilohertz tone, which is correct. The level is 3 kilohertz, which is correct. And we've got a bar chart here showing us that, and the RF power. We can then go to scope and sign, add signal to noise. Now, in the previous test, what I forgot to mention was SINAD, signal to noise and distortion. You would normally do that test using a test receiver. Could be any receiver basically, but you would get a receiver, say for argument's sake a scanner. You would connect up the receiver under RX test. You would input a signal at a given modulation level into that receiver, and then the AF level then from the receiver would be taken into the AF input here, and then you would basically within that be able to read the audio output then from the receiver and get the signal to noise and distortion. So you'll put in a particular level that it may say in the manual, recover the SINAD, say it said 15 dB, and then you would then do all that measurement on your reference instrument that you're using. So you would do all that measurement on that test set, you will get the level at 15 dBs at whatever RF output level it was given to get 15 dB synad. You will then move the transceiver over to this radio test set and perform the same measurement, the same levels as this one, RF level wise. You will couple the AF input here as well, and then you would see whether you got 15 dB synad. So that's one way of doing it. There are other ways, but so basically just comparing synads between the two instruments, that being your reference instrument and this being your repaired or maintained instrument. Now back to TX testing. The only reason my synad is displayed here is so that you can obviously do a signal to noise and distortion on transmitters as well. In addition to that, it's useful in duplex testing too, as part of the duplex test. So I can read the synad, AF volts, RF power and deviation, but in this context we're not too bothered about that at the moment. If you've read synad in the signal to noise, synad in the we've also got distortion as well. Again, in the receive test you can select distortion on and off, so you could put a distortion analyzer on, obviously produce a frequency and a particular distortion level, and then you could read that out on there and compare it against another instrument. So again, that's the basis of it. But under here, if we go back to where we were to start with, on the scope, now we've turned that scope into what is a demodulation scope. So we've got 6 kHz in the dotted lines, FM deviation. Excuse me. We're reading all the necessary parameters of frequency, so we could enter in TX frequency 300 megahertz, and that will give us the frequency inaccuracy. So if that's way off frequency, then we would need to adjust the reference oscillator internally again, just like we did when we did the receive test, when we're generating a signal out to the reference test set. If it was off, we'd have to adjust the reference oscillator to pull the analyzer onto frequency properly. We've then got the transmit power, which is reading correctly, the mod frequency is reading correctly, the levels reading correctly at 3 kHz, the distortion is 0.2%, which I'd expect it to be because the signal isn't distorted, and these are what this test set will be generating as well. And we've got the 300 Hz to 3 kHz filter. So that all looks good. Now you can vary that on there, obviously. I could go to, put in any frequency basically, or level right up to whatever it would recommend in the manual. You could change the AF frequency as well, and then check the level. Now according to that, we're on 5.1 kHz deviation coming out the reference test set, and on here we're reading 5.05 kHz. So that's bang on, I can't grumble. Can't grumble at all. Now under that test as well, there's the audio test, where we can now give an AF gen output, and that will be used in transmitter testing, where we'll connect the output this to a microphone circuit, and then as part of radio servicing it will give a particular FM deviation level out of a transmitter with a particular AF drive level. So we can look at that next to make sure that the AF output of the audio generator is functioning properly. So how we do that is we would simply move the BNCs over to the AF gen output. We will then connect the AF gen output of the instrument under test to the audio input on the HP8920 reference test set. Now we could go to, I think it's RX test on here. Oops, scope. Yeah, I'm in scope there, and then we would go to, for example, we could set the AF gen level on that. Let's have a look. Set mode, AF level 1 kilohertz, level 1 volt, and then we could verify that's been received on the instrument, which it is. 500 millivolts per division, so we've got 1 volt there, and then obviously we could vary that as well, the frequency output as well as the amplitude. So that confirms that the AF level coming out of here is correct. So that's part of that adjustment. If you needed to adjust that internally, you would do that with a potentiometer in the top. If you remember the cards that are inside with the blue pots on, potentiometers, one of those is for that, setting that level. So that would be where we would adjust that if we needed to do that. Okay, so now we've set up a measurement using the calibrated RF amplifier that we were featuring earlier, where we have the RF signal generator here, which is very difficult to see a display on camera, but basically I've set that up to 300 megahertz to give a 0 dBm output, which is coming down the cable into the input of the amplifier, and then on the output we've got the cable which goes up to the high powered RF port on the front of the test set. I've set it so that it reads 5 watts of RF power, which it's doing, and that's functioning okay. With no modulation on the carrier or anything like that, we're just reading transmit power. So I've got a 5 watt reading there. I can disconnect that now, and then I can now connect that to make a comparison of 5 watts with what the HP Agilence radio test set is saying. Now, contrary to popular belief, many of the instructions that you'll find in the calibration manual for the Marconi radio test sets doesn't recommend that you do all the RF power right up to its maximum rated 75 watts. It'll just say, you know, connect to source power amplifier to the Marconi radio test set and set it for, you know, 6 watts RF at whatever frequency, and it'll ask you to do that check across the frequency range of the test set at that 6 watt RF power. The reason why it does that in the manual is probably because this is a fixed attenuator that's behind the N-type, as we were showing in the internals of the instrument, and you know, it doesn't matter if you put 70 watts in, 10 watts, 1 watt, 3 watt, it's still got the same level of attenuation. So it just recommends that you do a low power RF measurement, and then you know, obviously that will suffice then for the rest of the range of the instrument. Once it's calibrated to that one level, it'll be fine with the rest of it. So yeah, it tells you how to go on in the manual anyway. So right, we've connected the SIG-Gen output now, again still through this amplifier, then back to the HP. So we'll just make a power comparison now and see what we're getting as far as wattage is concerned. Now I'm still on my duplex port here, so I just need to switch back to RF main. I think, where am I? Oh. TX test. I made an error here somewhere. Let's have a look. Where have I gone wrong? Not getting any TX powered measurement. I've got the frequency right. No, it's a bit differing. TX measure. Tune mode. I have no idea what's going on here. Oh, there we are. I'm on the wrong port. Switch it to the N-type port. So it says we're doing 4.3 watts on this instrument. So obviously it's you know, a little bit out. So that it's debatable whether we'd There's about 600 milliwatts difference, I'd say, there. So we'll just see whether or not that still applies. It could be a temperature thing, as the amplifier has been warming up while I've been gabbing. It may have reduced its RF output power, so that's again another thing. You'd normally fan cool your amplifier so they maintain a constant temperature as best as you can. So we'll just see now what that says. Ah, yeah, so it was a temperature thing, 4.5 watts. So that's another thing that you need to be aware of. Temperatures increase, the gains change, you know, settlement, all that needs to be taken into consideration. But as you can see there, we're getting 4.5 watts as it's nails on, damn it, what it was saying on the HP. So that is more or less that calibration done for the RF power. If that was off, way off, again there's a potentiometer on the board in the top for twiddling to adjust that back to what it should be. But reading 4.5 watts there nicely, and it's doing pretty good. So that's that. So further to the AF measurements we're making earlier, there's a sequential tones decoder and encoder in the Marconi, and we can test that as well. Normally we wouldn't need to test both sides, although we can, simply because if there's an error in one, there'll be an error on both sides, because it uses the same chips and tone sets to produce both encode and decode capability. So again, you know, if you've got a fault with one, you'll generally have a fault with the other. But under tones, we can select excuse me, sequential, CCIR. I'll set up CCIR on there to send a random code that I've typed in on the screen. So all I need to do now is we're generating a frequency at 300 megahertz at 0 dBm, which has been fed in on this port that comes from the source test set. I've turned the volume up so we can hear the tones, and now let's see if it decodes properly. So there we are. That's what we're sending, 1, 2, 3, 4, 5. And you can do that with all the different tone standards. I've selected 5 kHz deviation for the mod source as well when it sends the tones. But as well as that, I think on here I can select, if I can find it again, we're on CCIR. If I go down to it, it says, let's have a look here, there'll be DTMF, ZVIE, EA as well, there's EA, so we'll select that. We'll go back to send, so we can go to tones on here again, sequential, select EA for example, and then click send on there. So it's decoding that, doing that, return. Again, tones, I think there's a DTMF decoder as well, so any received data will be in here. So I'll just see if I can find DTMF on here as well. Blimey, oh, I know where it is. It's under here, DTMF, and then we can dial in a particular sequence. I think I've put a sequence there, as well as being able to dial things directly. So let's have a look, see what it does for DTMF. So it's decoded that. Likewise, we can do the same as well, where we're testing the output, the tone output to that, and that can decode what this is sending. So you do it both sides, transmit and receive, back and forth, and then you check that the data's been decoded properly on there. POX SAG, I'm not sure, I think under paging, let's go to tones again. No, I don't know if it's on this. I think it's under receive test tones. POX SAG, it can give a tone out, POX SAG wise, so I might want to have a look at that next. But I'm not sure on the decoder on this if it does POX sag. Let me just have a look. I think it'll be under receive, because we'll be... No, it'll be definitely be under transmit, yeah. Because we're sending a signal to the test set from the Marconi. We would need to go to tones. I can't remember how the damn I got to the tones now. Oh, there we are. Encoder, decoder. That were it, decoder. Then we would need to go to standards. I think there's a POX, there's a trunk radio one. Can't see POX sag there. It probably is there somewhere. MPT 1327's for trunked. DTMF function generator. Unless it's under sequential. It might be under tone sequence. And then it might be under there. No. No, I don't think I can do that on this. I think where the POX sags allowed on that. I'm sure you used to be able to test POX sag transmitters somehow under TX and then tones, DTMF, DCS return. I'm sure you can somehow on that HP. I'm sure I've tested POX sag transmitters on the HP 8920. There'll be a way I can get to it where you can go to receive test on here, then for pager testing, for example, for emulating pages, you enter your radio interface code, identity code, your RIC code. POX sag stands for Post Office, I think it was Communications Sub-Advisory Group, was POX sag. It's mainly the fire services that use the POX sag standard on paging, as well as other standards. But again, most paging operators that still operate use POX sag, and other paging standards at different baud rates and stuff like that, and speeds on whatever frequencies they're on. But you can then generate a RIC code and then send that to the HP 8920 to decode it. So that just gives you a little rundown of what we've done so far. But yes, it's interesting, but that's the end of the video now. I didn't want it to go on too long. It'll be way too long as it is, but at least it's a full featured video that shows the fault diagnosis, component level repair, setup, alignment, how you do the measurements on the test instrument. I've got somewhere the diagram and the technical information that shows you what keypad sequences to enter in to get it into the calibration mode for the receive signal generator, RF output levels, as well as other things that you can do in the digital memory. But that's beyond the scope of this video at the moment. If I do obviously get to that point in future repairs where it's found necessary to go into that menu, then I'll show that. But without the information on hand, I won't be able to do it in this video, because I need to find the info and what you type in to get it into that digital calibration mode. But it's not needed in this video anyway. I just wanted to show the basics of doing calibration, maintenance and repair on this kind of an instrument, and how you go about doing that. So with that, I hope you've enjoyed the video. It's certainly been, as far as I'm concerned, not so much about the destination but more about the journey. I think when we look back at what we had to deal with and the uncertainties of what might be wrong, and being chased around with regards to potentially what components have failed, and the fact that somebody else has been in the instrument before me and started to do some maintenance and then given up on it. I'm not sure what they'd done, but there were certainly components that have blown in the power supply which I've never had to replace before. Those diodes never ever gone prior on any of the repairs I've done previously. I've done hundreds of these. So yeah, a bit strange, weird. I think it's a lesson that, you know, for future, that if I get a similar fault, then I'll start looking in those similar areas, but more often than not it's not that, it's the transistors that are blown. I've never had any where the transistors have melted the insulators that bolt them to the heatsink. That's certainly something I've not had before on this instrument. Just seems a little strange that some of these faults were there, that, you know, several faults, there's 3 faults in total. Transistors are blown, 2 diodes have gone short circuit, and 1 diode had also gone short circuit as well. We haven't had any other problems with it really other than that, so I can't grumble. It's been a good video, and I hope you've enjoyed it, and thank you very much for watching. If you like the video, please subscribe. There'll be more repair videos to come, and I look forward to seeing you in the next video. Bye for